Okay, recording should be running now. And I suppose we can try sharing again. Where did the, oh, okay. Share pad. Okay. Well, let's see if that fixes it. There's a super annoying control panel for Zoom that just, I can't get it out of my way. And what makes it disappear? Well, I can live with that. So, good evening. Let's see, the bad news is I don't have your test graded yet. I'm finding that grading as well as other class-related activities takes a lot longer doing it online, which I've been told before by other people, but I'm experiencing it. So fortunately, next week is spring break, which gives me a chance to get caught up on my grading, among other things. So I apologize for that. I know you're probably all chomping at the bit to find out. Are we doing participation today? I'm not sure what you mean by participation. Head count, always. Everybody who hasn't already said something, say hi. Thanks for reminding me. I need to go back and check some of the more recent classes and see if the attendance records are more accurate now. Everybody else says that they get good attendance records. I get 3 people, and they join the meeting before the meeting time and they leave the meeting before the meeting time, and that's all I get. So something weird is happening there, and I need to try and figure out what's going on. But until that's fixed, this works pretty well. So yeah, we now have 20 of you. How many of you are there? Just out of curiosity. Well, the last thing I printed out, there was 31. That thing's pretty far out of date, though. Anyway, we got 20 of us. Good enough for me. We have a quorum. So, I guess we can start with questions on anything.
I have a question about stack pointers. This might be in the beginning, chapter 6, but stack pointers, does the value vary with each operating system? Or the stack pointer, the value, does it start with 0, or does it start with like a big hexadecimal value?
Okay, I'm going to unshare this screen if I can figure out how. I'm going to share my regular screen. Maybe. Okay. Let's go take a look at, let's see, where would I have put it? Lecture notes, the ISA PDF. I thought I had put some other PDFs out there as well. Maybe I haven't. Okay, so common, PEP8, CPU, simulations, memory map. Oh no, not Photoshop. I have to wait 10 minutes for it to start up and then I can shut it down. Well, anyway, oh, geez. Yeah, I'm going to shut this down and open it up with something normal. Okay, so this is the memory map of the PEP8. That is critical. When you asked the question, you did recognize that there could be a difference there. So our particular machine okay, it's actually the operating system of the PEP8. Okay, the PEP8 has memory from 0000 to FFFE. That's just all the memory. The operating system built in is divided up the memory in this fashion. And we talked briefly about the sudo command burn, which basically you can write a very large program in assembly, and then you can burn it and effectively completely replace this entire contents with whatever you want. In other words, you can reconfigure the operating system. Now, the basic machine language commands you can't change. However, several of those commands are labeled trap. And those commands, the machine language definition of the hardware is to go out to this trap handler area and find the appropriate code to execute that trap. So if I wanted to redefine some of the services my operating system provided, I would change the contents of the trap handler in order to redefine what those traps do on this machine. I could also change the size of the trap handler if I want to give up space somewhere else. I could make the user's memory space, which is actually most of it, it goes all the way up to FB. I could make the user memory space smaller if I wanted to provide more services in the operating system area. There's a lot of choices there. And so this is the basic map of the PEP8. It is really primarily the hardware's, or excuse me, the operating system setup. The one thing that is built into the hardware are these 4 down at the bottom. Okay, these are each 2-byte words, and so there's a total of 8 bytes there. And these bytes are fixed in the hardware. You can change the value when you burn it, but you can't change how these are interpreted. Basically, FC9B, okay, that is this address right here, FC9B. That bottom byte, or that bottom word, defines where the trap handler starts. The next one is FC57, which is right here. That second word up defines where the loader starts. The next one is where the IO buffer starts, and the last one is where the system stack starts. So if I wanted to reburn and change the operating system around, I could put whatever I wanted from from 0 up. And by changing these 4 values, the hardware would be able to figure out where things can be found. So the stack that we're talking about is the user stack, which, as things are set up right now, starts at FBCF. Okay, when it's at FBCF, it's actually the first byte of the system stack, but that is 0 for top of stack. Okay, the stack has nothing in it, and so its value is 1 below the first byte in stack memory. As soon as I add anything out of that stack, the top is going to move up into a reasonable place. So FBCF, which is in the 4th word up from the bottom here. I don't know if you can see my cursor rolling around or not. It's pretty small. I could put it over here. It's a little bit more visible. The FBCF down there basically says where the system stack ends and also where the stack pointer in our computer is going to be initialized. Whenever you enter a program, stack pointer is initialized to FBCF. That's just a given. If we wanted to be somewhere else, we could reburn this thing to put it somewhere else. I hope I covered the answer there. If you type it into the chat window, then I can look back and see if I answered everything or not.
Oh yeah. So whenever things goes on top of the stack, it will go into the user stack.
Yes.
Okay.
Right. When we use the command that we've seen that involves the the add to stack pointer and subtract to stack pointer, those commands are defined to refer to the user stack. Now, this is just the initialization of that stack, that location. Once it gets going, of course, our program is going to move that stack pointer up into the user stack area when we start having things on that stack. So yeah, that's ours. The system stack is handled by some of the commands. They are in that table of commands that we haven't used. Basically, the traps. Okay, when the traps occur, they will actually. The traps are basically function calls in the sense that we are doing function calls. We put stuff on the stack for local variables, and the stuff in the trap handler down here, those are functions. And when one of them calls another, and when it is called, parameters are necessary. Some of the functions inside the trap handler call other functions inside the trap handler. We need stack space for that. And the operating system, when you're executing the functions in the trap handler, they decided, the designers, that we do not want to add that stuff onto the user stack. Why? Because the user owns the memory from 0 to FBCE. That is user space. If we added trap calls into the user space, we would be writing into the user's memory area. Problem? Not normally, but let's say that the user knows what they're doing. Remember that question I asked about calculating how much memory is available up there in different questions. Okay, I told you how much stack space there is and so forth. What if the user is aware of that? In other words, they're writing a big program. They are working really, really hard to keep that program within this space. That can happen. And in that situation, we may have it such that my program takes up a certain amount of space, and the function calls that I've got in my program are going to take that stack right up to that limit. Better not go over it, so that I've used up all the stack space. If a trap handler kicked in, if I called a trap command and it wrote onto the user stack, it would start writing over my program space. And that would be a very bad thing. So the designers of this system said, okay, we will set aside space for the system stack for their own use. I don't remember the commands that manipulate the stack. It may be that they only happen automatically when trap functions are called, but that stack, it serves them there. So right, anything we do, user stack. Those are our function calls, that area. That cover it?
Yes, so thank you.
Okay. We are going to look about 1.5 chapters away. We're going to look at, we're going to talk about systems that are bigger than the PEP8. The PEP8 is called a uniprocessing machine. Basically, you've got one user program and it's right here. And that's pretty much everything there is, other than the small operating system support below it. It doesn't have any opportunity to do multiple processes. Like most of you have probably seen, if I do Control-Alt-Delete, I get the task manager. And these are all tasks. These are all programs or processes that are running on my machine right now. And I get freaked out by some of the names. They're really weird. But do I have it set to show? That's not even showing the processes from all users. Those are only showing the processors that are running on my behalf. So there are others that are running more just for Windows maintaining the system. Most of these processes are not using any of the CPU's time right now. They're idle, waiting for their opportunity to do their job fine. But the point is, all these are programs running. Windows is a multi-processing system. And so this whole model that we're looking at here simply wouldn't work. We're going to have to go to a completely different model where memory, operating system memory, user memory is allocated and managed in a very, very different fashion in order to handle that multiprocessing situation. Again, that's about 1.5 chapters away, and we'll be looking at how that works. So for now, yeah, this is when we're doing assembly level and we're doing our own function calls and things. That's our stack, the user stack. Everything we do is on that one. We do not have access. We should not have access to the system stack. I hope we don't. Okay, other questions? Excuse me. Okay, well, let's start moving forward here. myself set up again. All right. Right now I'm sharing my screen. I don't want to do that anymore. I want to share my pad. Last time I tried this, was it last week? I'm not sure. Maybe I tried it on my own or something, but it failed. And I'm not too sure why. So I was really kind of nervous today. But today it appears to be behaving itself. So that's good. Oh, well, that's kind of cool. Okay, sorry, you can't see that. It's the control panel for Zoom, and it just kind of floated down off my screen in a kind of a cool way. Okay, so chapter 7 is called Languages. Oops, I don't want green. That's my grading color. Languages, grammar and parsing. I have grammar singular, which is kind of weird. So in chapter 6, we talked about how the compiler, I'm sort of looking at my pad now. My back is halfway to the chat window. So if you ask a question in the chat window and I don't respond fairly quickly, tweak your microphone for a second and let me know that there's a question. Okay, so we've already seen basically what the compiler does. In other words, if you have a C++ program, it's going to convert it into assembly using the sort of techniques we played around on the homework that was due today. What we haven't done is to talk about, well, how does the language, or how does C++ actually look at a program and recognize those language constructs? Okay, we were using our own human ability to look at it and say, oh, that's an if statement. Oh, that's a function call. Somehow the compiler needs to be able to read your file one byte at a time and say, oh, that's an if statement. Okay, there's a statement after it that is part of the if. There is, generating all the assembly is one thing, but before you start the generation, you need to recognize what you're seeing, figure out what the parts are. And that's what this is. That description is the word parsing. Parsing is to take something and recognize what it is and break it up into pieces. Probably somewhere in your youth when you were studying grammars in the English sense, they told you things like, well, a sentence has usually a subject and a verb and a predicate. And I remember sitting in some class, probably around 5th grade, and the teacher would write sentences on the board, and then we would say, okay, I think this is the subject and that's the predicate, and that's, we would try to break that up into pieces. Maybe we had to recognize noun phrases and other sentence structure concepts. And so parsing is simply looking at any form of communication which is structured and recognizing how this particular written thing embodies that structure and has meaning. Okay, so languages and grammar are two aspects of the language that we are going to try to recognize. C++ is a language, and it is defined in a number of ways. We're going to look at those methods today. Grammar in our English sense is the rules by which we write our instructions when we program, or excuse me, when we speak. Okay, for humans, it's the rules we use to construct a sentence. In language theory, or in programming, basically the word language refers to something like, for example, C++ And the important thing about it is a word of my language C++. Actually, let me get a little theoretical here for a moment. A language is a set of words. Yes. Now, this is not the English definition of the word word. This one is really strings. So, for example, if I had a string quote, the dog jumped over the fox. Okay, in English, we would say there's 5 or 6 words there. In this language set, okay, my language is English, so I can have example C++ or English. And when I talk about a member of this language, I'm not talking about a word in the dictionary, I'm talking about an entire sentence. Okay, so language is a set of words. We might call it a sentence. In C++, we would call it a program. So take an entire C++ program, all the characters that make it up. Forget about words for a moment. Forget about the different lexical distinctions of identifiers and reserved words and all that stuff. It's just a sequence of characters. And certain combinations of characters in a file make up a valid C++ program, and other combinations don't. If I have a file with ABC in it, that is not a valid C++ program. Okay. There's a number of things that the file could start with. It could start with include, it could start with a comment, it could start with main or int main or something like that. There's a lot of things it could start with and a lot of things that it can't. So a language is a set of words, and the words are entire programs. So when I talk about the language C++, what I'm saying is a set of all possible forever programs in the language C++. This language, C++, is infinite. C++ is infinite because there's an infinite number of programs. Be careful when I say that. Every individual program is finite sized. Okay, a program has to actually have an end some point, but there is no upper limit to program size. So as long as I'm allowing programs to get bigger and bigger and bigger, there's an infinite number of them. That's what I mean by that. Okay, so we have languages. Parsing is looking at the individual parts that make up a valid word. Let me write that down. Parsing is looking at a word, which is basically a text string. And recognizing or defining a program in terms of its parts. Okay, we're going to look at a bunch of cases that are a little bit simpler than C++, because C++ is a pretty complex language, nothing remotely like English. We could define English using the things we're talking about here. Okay, in the case of English, a word is actually a string which consists of a fully grammatically correct English sentence. The language English, the language C++, there is no semantic meaning behind these words. It simply is a set of words. Okay, the compiler is going to recognize a word as in or not in the language. Is it a valid program? If it's not, you get some kind of a compiler error. If it is a recognizable word, in doing that recognition, it has found parts. It's found main and parentheses and braces, and they're matching and everything is good. Okay, if all of that is identified by the program, the compiler, then we humans have built in the idea of the semantic or the meaning behind that word by saying, okay, when you see this construct, you generate that machine language or that assembly language. Okay, basically what you did for the homework that was due this week. Okay, you recognized the C++ command structure and you took each piece of that and hopefully followed the formula I gave you. It's very formulaic. It's all formulas. Every single construct in C++, there is a rule for substitute. You know, when you see that in C++ source, output this in assembler. I've gotten a lot of email. I was feeling very loved over the last several days of people asking questions about that assembler question. And a lot of the times my answer back was basically, you didn't do substitutions. You didn't take this command of C++ and translate it using the form that I showed you. Okay, it's a very, in some ways, stupid translation. Okay, the recognition is not stupid. That's hard. That's what we're going to be looking at. But the actual translation, there are very simple rules for translation, and they must be adhered to. Otherwise, if you try to translate a larger program, it's not going to work. I saw a lot of pieces, the stack adjustments, the return value processing, a lot of these things were sort of ignored and people just wrote assembly which produced the output or tried to. And that's not our goal here. Our goal here is to produce, it was to understand the way a compiler would do it. And now we're going to look at, okay, we're not looking at the output anymore, the assembly that it would produce. We're looking at how did it recognize the structures, and it has rules for outputting assembly for each of those structures. We're looking at the recognition end now. Okay, so simple examples. Excuse me. Okay, a set of words. A, B, C, B, 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 C, and let's just stop right there. This is a language, a relatively simple one. Okay, it's got three members, three elements, the string ABC, the string BBB, and the string C. Okay, this doesn't have any structure like C++. We've got to work our way up to that. But this is an example of a language. A simple finite language. Oops. Okay, let's do another one. A, AB, ABB, ABBB, dot, dot, dot. Okay, this is an infinite language. The trick is that this particular language, so this one has a little bit of structure. It could be described in English with the phrase, okay, first of all, the alphabet of my language is A and B. Those are the basic atomic parts. And the one above the alphabet would be A, B, and C. Okay, a word consists of characters from the language's alphabet. Okay, haven't really gone into that yet. Okay, so first example, ABC is the alphabet. Second one, it appears that only A and B are part of the alphabet. You will do an upper division class in formal language theory, where you will spend the entire semester dealing with languages at this level of complexity. In other words, not very complex. Okay, generally you're only going to have A and B, and for the most part you will address infinite languages, but you're going to look at different ways to make them jump through hoops and different ways to recognize patterns in them and all kinds of stuff like that. That whole class is basically, it's about a number of topics, one of which is how a compiler works. You learn a lot more about the processes it's going to use. It's also, strangely enough, a completely different direction. This is the beginnings of formal computation theory, which means these definitions of languages lead us to an understanding of what can and cannot be computed by a computer as we know the word. Ultimately, these languages can be representative of computers themselves, and certain properties that we can deduce from the nature of these languages tells us what computers can and can't do. Okay, that's going too far. You'll look at that when in an upper division. Right here, we want to deal with it on a little bit simpler layer. So this particular example, the second one here, the infinite language, I'm hoping you can all handle the ... Would anyone care to share what the next word would be? Either speak or text or chat it. A, B, 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 B. 4 B's. Yes, good job, you pass. Okay, 2 people pass. All the rest of you, you're losers and you failed. I don't mean that, of course. Too late, Tyler, I already called you a loser. All right, so that's not the next word. That would be somewhere out there. Maybe that was, I assume that was a joke or something. Yeah, that would be somewhere in the language. It wouldn't be the next one. By the way, there is no order to the language. Okay. You may not have looked at sets too much yet. You will look at them a lot in Computer 140. If you're taking that, you may have already looked at some set stuff. Basically, a set is an unordered collection. There is no, this one is first, this one is second. We don't have 2 words A in the language. That's called a multiset, and we're not doing that. So any given word occurs in the language exactly once, or 0 times if it's not in the language. Okay, so the ... I call that an intelligence test. And this is not the way we define things. That is not appropriate. Because just depending on how complex I make this pattern, you may or may not figure out what the ... is. There is no algorithm, no program I can write that will look at any arbitrary sequence that I write, even if that sequence has a logical structure. I can't guarantee to write a program to recognize that logical structure when it gets to the ... and figure out what the next thing is. An example of that, if I give you the numbers 1, 2, 3, 4, what do you think the next one is? Another intelligence test. Anybody? 1, 2, 3, 4. What's the next number? Probably 5. But you're making an assumption that my pattern was actually a first degree, excuse me, first or 0? It's no more than a first degree polynomial defining that sequence. If I go up to about a, let's see, 1, 2, 3, 4, if I go up to about a 5th degree polynomial, I can produce a sequence from that, which would start with 1, 2, 3, 4, but would diverge after that point. Okay, if I have a more complex polynomial with more ups and downs in the curve it defines for different values of x. And so there's not a whole lot of guarantees here. Any finite example cannot guarantee, it is not a solvable problem to determine the pattern from that. So the ... is wonderful for human beings. And if we're lucky, we get them right. As we get older, we find this harder and harder to do because our ability to recognize those patterns drops over time. And it raised over time when you were younger. So you guys are probably still in the boat where it's going to get easier and easier for you just from age and experience, but also from practice in various classes. For me, I'd like to think it hasn't gotten harder yet. I haven't really tried anything hard for quite a while. All right, so yeah, that's an example of an infinite language, but it's not an appropriate way to define it. That's what I'm saying here. This really does not clearly define what it is. It's sort of like the question, if I want to define addition for integers. Okay, I want to define the addition function. It's an infinite definition because there's an infinite number of integers I can add together in different combinations. And so there's no finite way I can describe that, and dot, dot, dot just doesn't cover it. After I get to 144, 12 times 12, dot, dot, dot doesn't really say what the pattern was for those calculations. There's no guarantee. So we need some way to be able to define infinite languages with a clear and unambiguous definition structure. This semester, we're going to look at two such methods. One is called a grammar. The other is called a finite state machine. There are other methods that you'll be looking at in the separate division class, specifically something called a regular expression. And between those three, you'll start looking at their relationships between them and start finding out some things about computability as a topic. Okay, each of these three ways to describe a language is itself or can be applied to model the concept of computation. That's where this ends up going. Any of these three can model computation. And the interesting thing is, if you apply any of the three to the question of computation, you bump into exactly the same limits on what can and cannot be computed. Three extraordinarily different ways of defining a language all end up bumping the same limit. And this is considered not proof, but a strong indication that maybe there's something universal going on here. And by the way, there's a fourth method of defining computation that the mathematicians invented a long time ago called recursive functions. It goes back to recursion as you know it, but taken to a degree that's absolutely terrifying. They all bump into exactly the same limit of computation. And so we tend to say, there may be something going on here. This may actually be a true limit. We don't know. Could be that just all four methods are limited by our human understanding, and a Martian might look at it a different way and find some more powerful computational model than we have. But at least for us humans, it looks like we may have found a universal limit. Okay, enough theory. So our goal for today is basically to look at two methods of defining language. And the first is a grammar. That's where the grammar is kicked into here. A grammar is a set of rules for defining a language. Let me write that on this page, and then we'll go to the next page. Because that's the only thing I've talked about parsing, and I've talked about languages. And so I'm going to say a grammar is a method of defining languages. It will handle both finite and infinite languages. No problem there at all. A compiler reading a program and the program, remember, is word of language C++, tries to find, okay, that was badly written, tries to find proof that the program or word is in the language by showing that a grammar matches this word. In other words, if I have this rule for grammars that defines a language, defines a language, and you give me a program, what I'm going to do is I'm going to say, okay, to find out if this program is actually correct, is it actually a fully correct program according to the rules of C++? I have a grammar that defines C++, and I actually want to show by applying the grammar that this word is in the language. Interestingly, okay, I know for a fact that if there is a word in the language, there will be a grammar construction to show that. If there's a word not in the language, I have a more difficult problem of showing that no application of the grammar can produce that word, which would say the word is not in the language. Okay, so moving ahead here. So therefore, a language can be defined as all words that match the language's grammar. And match is a word I'm not really comfortable with. Grammars are not unique, by the way. I can make several different grammar, probably an infinite number of grammars for almost any language. But a grammar defines the language. Okay, going the other direction, if you said, hey, I want a programming language that has the structure, I would take the English concept and I would go out and write a grammar describing the language that I want. With that grammar, I can now talk about compilation possibilities. In the early days, Fortran, COBOL, they basically just sort of wrote down on paper, okay, we want these kind of things in the language. And then they just went out there and sort of punched their way through writing a piece of code that would read and translate. They really didn't know what they were doing too much yet. The syntax of their languages was ridiculously simple. It was a single sequence. We didn't have the blocks or the if then else's or any of the complicated stuff. We didn't have function calls, really. And so they didn't need these grammars. As you start getting more complex like C++, you need something that can define the complexities of that language in a clear manner. So, okay, so let's define a language. Let's go back to that ABB language again. Okay, I'm kind of jumping into an example, and I'll sort of step back and look at the pieces. Okay, the alphabet. And our usual symbol for alphabet, just in case you care, is capital sigma. I don't have that in my notes here, so maybe the book doesn't mention it. Okay. So my grammar, so in this case, it is the set A, B for this particular. Okay, the grammar is a set of productions. Okay, notation. I will use lowercase for members, for members of the alphabet. Which are called terminals. I will use uppercase for what are called non-terminals. Okay, and I will have, oops. I will have a set of non-terminals. So I'm going to go with my non-terminal set. Will be S and B. Now, this is sort of like programming with single letter variables. When you get into like defining a language like C++, your symbols are multi-character identifiers. Okay, it gets bigger and they become far more descriptive than this. We actually often use left and right angle brackets around character strings to say this is a single symbol, a non-terminal.
Is there any reason why you chose S and B, or it's just
there is
chose any letter? Okay.
There absolutely is, and you'll see it in just a moment. Good leading question. Thank you. Okay, so I'll come back to that though. So our grammar consists of, or no, also includes also has a set, lots of sets here, it's very set theoretic, of productions. Lots of words too. Product, D-U-C-T-I-O-N-S. Okay, a production for the purposes of what we're going to discuss, a very simple form of grammar. We're going to have a single non-terminal, to a string of terminals and non-terminals. For example, I might say S goes to B, A, B, S, little b, S. Okay, the left-hand side is a single non-terminal from that set N. The right-hand side is a string of terminals and non-terminals. So I can pull from the N set. I can also pull from the sigma set, the alphabet. There are more complex grammars where the left-hand side can be more than one non-terminal. And so you say, if you see this string of terminals or non-terminals on the left, they turn into stuff on the right. That is called a context-sensitive grammar because you have to look at larger strings, which is a sort of a context. We're doing what's called a context-free grammar. And the context-free grammars are perfectly adequate for describing any language we want to describe. I think the context sensitives are capable of slightly greater description. I'm pretty sure they are, but that's not important to us. Okay, so we have a set of these productions. Okay, for my language, which is I'm going to forget the quotes now. Okay, now that is not a legal description. Oops, I'm running out of page. Okay, so we'll start it there again. For L equals A, AB, ABB. My production set is going to equal the following. I will have S goes to A, B. S goes to A. B goes to BB, and B goes to B. That's a complete definition. So we have a set of alphabet, we have a set of terminals, we have a set of non-terminals, and putting those all together, we get the set of productions. I'm claiming that I can use these productions, these rules, to create every word in my language, which shows that the word is in the language by definition, because the grammar defines the language. And I will not be able to create any word which is not in my language. For example, let's do ABBB. Okay. Now, one other thing we need, I'm going to go back to the previous page. Where's my set of non-terminals here? Oh, there it is. Okay. So the set of non-terminals, one is identified as the start non-terminal. There's your S. If I was talking about a C++ language, a far more complex situation, my start symbol would be a non-terminal called program. And from this start point of the non-terminal program, I should be able to apply a series of these productions to produce any and all possible legal C++ programs. In this case, S is my start symbol. We usually S for that when we're just playing around with these small ones. And so from S, I can produce any word that is in this language, and I cannot produce anything else following the rules of productions. So here's how I'm going to do it. I'm going to start with S. That's pretty easy. And for reasons that will become hopefully clear. Okay, I'm going to underline it, and I'm going to pick one of my productions that matches that. In other words, I'm going to take the S on the left. That's my start point, and I'm going to apply one of the productions to it. Okay, I'm going to apply the one that goes. Okay, now if I apply the second production, S goes to A. That just says A is in, oops. The language. That was the first word of my language. Okay. The string A is a word that is in the language. It's a terminal letter. I can't do anything with it. I'm done. On the other hand, if I start with ABBB, let's do that one. S goes to A capital B. Okay, I'm going to use that production this time. Now, terminals are terminal. They're done. That's why we call them terminals. They don't go anywhere. They're just there now. They're dead weight. Okay, but a non-terminal, I can apply a substitution. So from S, I get the string AB, and I'm going to underline. So S got substituted to AB. On the right-hand side here, I'm just indicating this is not necessary but it's just helping out other human beings to see, because I could get a long string here with lots of non-terminals in it. Okay, it's kind to underline the one that you will apply the next production to. So this one is going to go to, now the A's can't change. That's there, it's going to stay there. But the B is going to be, I'm going to use the third production, and so that's going to become B. If you start thinking ahead, what is the sign after ABB? In the for line or the example line or somewhere else? Oh, no. In the for line. After ABB, that's ... It's just a really bad ... Go away.
So P equals the curly bracket, and everything in that curly bracket, S just means A, B, or A capitalized B, or S can just means A, or B can just means lowercase b, capital B.
Say that again.
How did I put it?
It gets weird.
So S, the big S, it translates into lowercase a.
S is replaced by. S produces A and B. That's why we call it a production.
Okay.
Okay. So anytime you see an S anywhere in a string, it can be replaced with AB or it can be replaced with just an A. Anytime you see a B in a string, it can be replaced by little b, capital B, or by just a little b. And those are my 4 productions. I can only apply those 4 rules. Right. So we start with the string containing S. That's our rule. And then I'm going to use the first production and replace S with AB. So now I have the working string AB. Okay, I have 2 symbols in that string. The A is terminal, I can't touch it. The capital B, on the other hand, I can apply a substitution to that.
Oh, I see.
Okay,
right.
So that's why I drew those little lines there. The little A just stayed untouched. The capital B, I applied the third production and got lowercase b, capital B. Okay, on my working string now, little a, little b, capital B, I've got a non-terminal there. Non-terminals are not terminal. They've got to go somewhere. Okay, I continue this production system until I have no non-terminals on the right, or on my working string. Okay, when I have no non-terminals, I have a word in the language. Okay, so this time I'm going to apply it to B. I'm going to use the same production again. So I have the a, little b that was there before, and this B is going to go to little b, capital B. And finally, I'm going to apply the other production to this capital B, and I get A, B, B, and I just get a B using that 4th production. What's going on? I am changing my my screen, and you're not seeing me add additional things on there. My screen on my computer is not showing the changes I just made.
No.
I wonder if somehow I didn't lose a share because it's there, but it seems to have frozen up somehow. Let's try stopping the share and reinitializing it. The Microsoft solution, right? Okay. There, stuff just appeared. Okay, so we start with S, that's the rule. We replaced S with AB using the first production. You can use any production that matches a non-terminal. So this is my working string. I've only got the B in it. And so I'm going to replace that using the third production to get to BB, and that A is still in the working string. Terminals just sort of ride along. They don't go away. Okay, in the last example, did you carry the A? Yes, I carried this A to here. I carried it again to here. It's not being changed. I can only replace non-terminals. Okay, so I get to AB, capital B. I apply the same replacement again. That AB remains here, and this capital B turns into B, little b, capital B. Thus the name B in my non-terminals. Okay, it generates B's. That's its job. It generates one or more B's. Okay, so then I have A, B, 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 capital B at the end. And I apply, this time I apply the fourth production to this B, which is just go to a single terminal B. So that B turns into this B. I have a fully terminal string now, and that string is in my language. Okay, now again, this grammar defines my language. It defines it completely in the sense that any word that can be reached by a production sequence is by definition in the language. And although harder to prove, any word that is not producible, that's the hard part. Okay, if to show that, here's some word and there is no combination of productions that will reach that word. Okay, it's not, well, let's try a combination and I didn't reach it, so it's not there. There may be some alternate combination of productions that could lead to that word. Okay, this is a good method of showing that a word is in the language. It's not very good at showing a word is not in the language because that's a negative proof and they're extremely difficult to do. Okay, that's a limit of the grammar system. Ultimately, yes, we can produce a proof that a word is not producible by a grammar, but it's not somewhere we want to go. It's way too hard. Fortunately, these grammars can become actually, even with a simple format, one non-terminal to a string, and you can have more than two, more than one. And in fact, by the way, just note, lower lambda equals the null or empty string. So for example, if I had A, C, okay, back up, capital C, not a part of the example above, A, and I had the production C goes to the null string, my production would go to AA. In other words, you're allowed to have a non-terminal that can go to nothing. That would have allowed for a slightly easier production system up for this language up here, but I didn't want to get into the null string yet. Okay, so you're allowed to have a production going to one or more characters, both atomic and terminal and non-terminal. And you're also allowed to say, if I have this non-terminal, I can just drop it out. That's allowed. Can this grammar system be applied to every programming language? My gut reaction is yes. Okay, the fact that you call it a programming language, okay, this is what language means, people. This is exactly what the word language means to us. And so whether it's a programming language or not, anything that qualifies to the word language can be defined by a grammar system. Now, I mentioned this grammar system, our productions are of the form single non-terminal to a string. There are more complex production systems that we're not using. Okay, for example, I could have over here on the left-hand side, S little a. And that says only if you see an S with a little a can you replace those two things with things over here. In effect, terminals can be eaten by productions. Okay, that gets funky really fast. Okay, we're not doing that. To define programming languages, we don't need that ability. Okay, every language that I can conceive of, we don't need that. This system, it's called a context-free language, which I will not use that phrase in class. This is just the only grammar we know. And it can produce, yeah, every programming language you've ever seen without question. Something like Fortran, trivial. Something like C++, a little harder. But ultimately, we can do that. I'm going to give you some examples to show you how we might start addressing something like C++. We got to work our way up to it. Okay, so the null thing is allowed. Notice the example I gave up above, my 4 productions, I didn't need the null. And that's kind of an important thing. Generally, you don't need the null. It's just a convenient shorthand. This is, again, lowercase lambda if you care. And in many contexts of programming, this means the empty string. Okay, capital lambda generally means the empty structure, referring to things like stacks and queues. All these symbols have meanings to us. Okay, so null or empty string. I can do any grammar without the lambda that I can do with it. The lambda is just a convenience. It makes it easier to describe things sometimes. There is only one class of languages. When I say any, I'm lying. If the language I do not need lambda unless my language includes the empty string. Okay, we hadn't touched that before. I said a language consists of words. Programming people, when we talk about strings, the empty string is a thing. When we talk about numbers, 0 is a thing. You don't just assume that when you're processing numbers, it's always positive. Okay, unless you have good reason not to, you deal with zeros in programming numbers, and you deal with empty strings when you're programming string data, because they can happen unless you make sure they can't. So anyway, our languages here can have an empty word in them. That's okay. And if that is the case, I need one production, S goes to lambda. It's the only way to get it. That original start symbol has to go to nothing. I don't need it anywhere else. So we don't need it except for a language that contains the null word. Fortunately for C++, I don't believe an empty file is a valid C++ program. So we technically would not need the null to describe C++, but again, it would make it more convenient. Okay, so a couple of other things came to my mind while I was just talking about that. Other sort of little bits and pieces that are useful. I do not need lambda. Okay, unless it's probably not readable. Let me fix that for you. See, I can write sort of readably when I try. Oh yeah. Empty language. Language contains one word or element, which is the empty word. Okay, they're not the same thing. This is a language that has 0 members. Think of an array, a vector array, and its size is 0. That's this one. Okay, a vector array of strings specifically. Okay, if I have an array of strings and its size is 0, that's what we're looking at here, the empty language. Okay, if I have a vector array that has 1 element in it, its size is 1, and that 1 element is an empty string, a string of length 0. That's a string, and it's a member of my vector or my array. So that's a language contains 1 word or element of, gosh, my writing is, I can't even read it. You guys should really keep me honest here. Oh, that actually wasn't of, that was just a colon. A string of length 0. Okay, so gave you a sample grammar for that language. Gave you a few little sort of details and additions that we can use if we want to. Questions to that point? By the way, that's it. From this point forward, as long as we're talking about grammars, it is just technique. How do we produce a grammar for a given language? And we're going to produce grammars for several other languages. I don't have a rule to give you. All I have is, here's some examples. This is sort of like programming. I mean, we do have combinations and patterns in programming, and we teach you those when we teach you programming. But ultimately, when you need to write a program, it's up to you to put the pieces together and figure out the right order to make things happen. That's kind of the same thing with the grammar. It's an acquired skill. It is, in my head, the same skill as writing a program. Pop quiz. How many people thought that writing assembly was the same as writing a C++ program in terms of the skills you needed to write it? Not seeing any answers. Eventually, you'll see them as the same thing, unless you give up computer science. They're both writing programs. They're solving. They're coming up with a way of expressing a certain solution, and the method of expression is open. Okay, using C++, that's one language of expression. Using assembly as a language of expression. They have a lot of similarities. Grammars are another language of expression. And it's just a matter of taking the grammars, putting them together. I put these together using skills that I built, that I use for programming. There is a transfer of skill there once you get comfortable with it. So right now it might look pretty mysterious, much like assembly did and probably still does. Eventually it becomes easier and easier. Okay, so let's do another example. L equals B, 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 dot, dot, dot. But in addition, B, A, B, A, B, B, A, B, B, dot, dot, dot. Also B, A, B, B, A, B, 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 A, B, B, dot, dot, dot. Okay, you might not be seeing exactly a pattern here at this point. Basically, it is all words. And the English, of course, is as weak as that other thing, the dot, dot, dot. But it tends to work a bit better for humans. All words without 2 A's in sequence. Okay, what I was shooting for up there was looking for combinations of A's and B's to where you don't allow 2 A's to happen one after another. Okay, so I had no A's, I had 1 A. I did some more 1A stuff to show that it doesn't have to be the second letter. And maybe if I was to add one more here, B, B, A, B, A, B, A, B, B, A, B, 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 A. I'm simply guaranteeing that A never happens twice in succession. This one's going to be a little harder, actually. I may have bitten off more than I can chew here. I'll have to be a little careful. I might screw up a couple of times here. We'll see how this goes. Okay, so my productions. Now notice I'm not, okay, I didn't define the alphabet. It's A and B. You can determine that from the example pretty easily. Okay, we're kind of going with that. You should be able to figure it out from what you're seeing. My production, I'm going to make up non-terminals as I go. When I'm finished, I'll say, well, those are my non-terminals. We start with S. Goes to, I probably won't be drawing the little set symbols forever. We just write, here's a list of productions. Oh yeah, previous line. Well, I'll do this one without, there's another improvement we can add to it. I'll do this one without it, and then, okay, give me just a few seconds here to think about this. A, S goes to B. A goes to little a. A goes to little a, B. S. Actually, make that a capital B. No. Yeah, capital B. Let me think about this a second. That might work. What I'm shooting for here is, okay, no two A's in sequence. So S goes to capital A goes to little a. That gives me a single A. S goes to capital B. Oh, I didn't define B yet. Okay, that's embarrassing. I want capital B to generate. The interesting thing here is that S is sort of representative of the entire language. From S, you can produce all words in the language. But every single non-terminal produces, if you start with it, it produces some set of words, and that non-terminal can be characterized as that set of words. I'm not too sure how I would characterize this exactly. Let me write B down. That one's pretty easy. Oops. B goes to little b. B goes to little b, B.
So this is just a made-up grammar system you use for a language that would not have consecutive A's?
Yes. This, to me, this is writing a program. Okay, it's a little different than to me, assembly and C++ are almost identical, almost. This is a programming problem. I need to come up with a way to describe a sequence of rules, which when applied will produce the words I want.
Okay.
Okay, it's a programming task. It is less close to writing C++ or assembly code. But ultimately, some of those skills will transfer. Okay, so this to me is a kind of a program. It's just a little bit further out than a whole lot further out than assembly. The purpose of this is to define a language. So let's just look at B for a moment. If a B appears anywhere in a working string, what can it produce? It can produce one B. It can produce two B's and go back to B, or it can produce one B and stop. It can produce a B and start over again, which I can get two B's. Or I can produce a B, go to this one, and then go to this one again and get two B's, and then three B's, and then four B's. I can get as many B's as I want and finally end up with the single B. Sooner or later, I have to come to this one with no production, with no non-terminal on the right to finish it. Okay, the B productions produce one or more B's. capital B produces the language of one or more Bs. Capital A produces the language of every word that starts with A has nothing following it, or capital A has one or more Bs, and then we can start over. Can I, okay, I can end with an A, I can end with a B. Can S produce an empty? No, it can't. So I may need S goes to lambda. Just throw that one on the end there. And you're not seeing it again. I wish I knew why that's happening. Okay. Okay, that's one way to do it. Okay, so B produces one or more Bs. S basically says anytime an A occurs, you either end it, no more word, nothing after that, or you have that A. So A says I'm going to get an A, but after an A, I either end it or I have at least one B following that. And I can repeat the process again if I wish. Can I get from here to AB? I'm not seeing a path to AB. So maybe I need to say, oh wait, yes, I can get an AB. Basically capital A goes to ABS, B goes to single B, and S goes to nothing. That bailed me out of a couple of problems. So if I have a word like,
I think if you start with B, I don't think you can get to use A, B.
Huh? No, if I start with B, I only get one or more Bs.
Right.
Okay, so we have to start at S to get A's into this mix.
Oh, you always start with S, right? That's right.
You always start with S, okay. But what I was saying was that any non-terminal could be viewed as describing its own language, which is a subpart of the overall language we're shooting for. Okay, if you look at all these examples up here, we have A's occasionally interspersed, and we have one or more B's between them. And so I have a non-terminal for producing those B stacks. And then I just have to have some way of mixing the A's and the B's together to guarantee that two A's can't happen in a row. I'm not going to have this production for A's. It would allow multiple A's in sequence. Wherever I have an A, I either terminate it or I make sure that at least one B follows it. I could probably do this simpler if I sat down and thought for a moment, but I'm just going to let it go at this. I'm sure I could do it simpler than this if I thought about it. Okay, so let's pick a word and show that it is in the language. Example word. Let's do B, B, A, B, A, B, B, B. Shall we end with an A? Sure. I should be able to start or end with an A and make it work. If I started with an A, I would go S to A to A, little a, and then the BS would generate anything that follows, making sure that there is at least one B before the rest of S starts. Okay, so this is recursion right here. Okay, S goes to A goes to ultimately S, and S starts over again. So this language has a recursive definition. This is an example of a recursion applied in this context. Okay, I can't see what I'm doing here. Okay. Got these chat screens and things in my way. Okay, so I got B, B, A, B, A, B, 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 bunch of B's, A. So can I get that? S goes to, see, we're starting with a B, so we'll go to capital B. And then we want another B in there, so we'll go to little b, capital B. Okay, I've got a problem. Got to modify my things some more. Okay, so that's no longer one or more B's. Okay, so I got a B, a capital B, and an S. That capital B is going to get me the B's I wanted. So how many B's did I want when I started? 2 of them. Okay, so B, the big B is going to turn into a single B, S. So I replaced S, I replaced B, I replaced capital B here, and I got to here. I will replace S in the next step. Okay, so this is going to go to BB, and S I will replace it with, I want an A now, capital A, which goes to BB. All those non-terminals just keep carrying through. We can't get rid of them. BB, okay, capital A goes to A, capital B, capital S. Okay, how many B's do I want there? 1. Okay, so that goes to, we'll replace the B. This is where the underlining starts kicking in. Okay, I had capital B, capital S here. I'm just helping you out a little bit by saying this is the one I'm replacing here. So the S remained unchanged. Down here, I'm going to replace this B, the S will remain unchanged again. I tend to do my derivations or production sequences always working on the leftmost non-terminal first. When I generated this, there was a certain thought process I was going through that leads to a leftmost derivation. That's actually a thing we talk about. Okay, so that B is going to turn into a single B. So I end up with BBA. Okay, the big B turns into a little b, and then I got the S there. Work on that one now. We're looking for an A, so that's going to go to BBAA. Wait a minute. Sorry, I left out a B. Little b. Okay, now A. That one's going to turn into B, B, A, B. Oh, that one always gives me an A. The capital A always gives me something starting with an A. And then another BS. And I will replace, okay, let me rewrite that one a little bit cleaner. B, B, A, B. Okay, this A turns into ABS. Okay, I'll work on the B. Okay, after this point, how many B's do I want? 3 of them. Okay, so I have B, B, A, B, A. Okay, that B turns into BB. The S is still there. We'll work on that B again. Goes to B, B, A, B, A, B. Okay, that B is going to turn into another B. And Okay, that's B, B, S, and there's another S there. Okay, this B here turned into BBS. Okay, this S is still there. So I get two S's in a row here. Is that going to cause a problem? Yes. I still don't have a valid grammar. Because if I have two S's in a row, with one S, I can produce something that ends with an A, and with the other S, I can produce something that begins with an A. So I failed. Give me a second. Okay, I'm going to start over. I wonder if there's any easy way to delete this stuff. Yes, there is. I will, uh-oh, you're not seeing the updates again. Okay, interestingly, I swear I drew on that.
Professor, I think I was able to finish it.
I can finish the derivation. The problem is that when I reach the SS here, this will allow me, yes, I can get the derivation of that word, no problem. But I'm looking at this now, two S's in a row will allow me to put two A's in a row. So the language produced by this is not what I'm after. Does that make sense?
Yeah, but
okay, because SS, both of those can each go to capital A, little a, and I get two little a's at the end there. So yes, there is this language, there is a derivation to that. So this word is in that language, but there are words in this language that I don't want. My production rules are allowing things. This is the sort of common human error that happens with these things. It's easy to make rules that produce what you want. It's harder to make rules that don't produce the stuff you don't want, because the definition of language is every word that can be produced is a member of the language. So we have to make sure that we can't produce something we don't want. I X'd out this page. I will delete it before I post this. I'm going to start over. And so I'm going to say example, all words. I'm not going to try drawing the example words this time. Without AA in them. Anywhere. In other words, no two consecutive A's. Okay. I don't think well when I'm in lecture mode. S goes to lambda, because an empty word is allowed. S goes to A. S goes to A, B, S. B goes to B, B goes to B, B. Okay, let's try doing our derivation with that one. I'm going to make a slightly shorter word. A, B, 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 A, B, A. Okay, so we have S goes to little a, and BS. Yes. Okay, that goes to, I'll work on the B, little a, 1B, B, and that S is still hanging off there. Okay, A, B, B. This B will get replaced by, how many do I want? 3? Okay, B, B, capital B, S. Goes to, oops, I lost my A there. A, B, 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 and that S is still hanging on. Yeah, I think this one's going to not let me produce anything I shouldn't. Okay, replacing the S down there, I have A, B, B, B. And so from this point, I'm starting over with S basically. And S can be more B's, which is fine. It can be lambda, which ends it there. Or since I guarantee there's at least one B to the left of it, I can start up with an A again. So this S is going to go to A, BS. I want a single B there. So that one is going to turn into A, B, 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 A. Okay, that B turns into B. And that S is still hanging on. We'll replace that with A, B, 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 A, B, A. Okay, so there's a derivation that proves that that word is in the language. And again, it's very difficult to show any word not in the language cannot be produced by this. That was my error in the previous page. I produced a grammar that accidentally produced things that I didn't mean it to. This one is simpler. It's easier not to screw up when you go simpler. Questions?
So you just cut it off when you converted the last S to the final A. You just cut off the rest.
I used the second production.
Oh, the second production. Oh, I didn't see that. Okay.
That's even when I underline the one I'm going to do the substitution on, you still have to figure out which production I'm going to use.
Right.
Some people write above the arrow, they number the productions 1, 2, 3, 4, 5, and then they write above the arrow, they underline the non-terminal they're going to replace, and over the arrow they put the number of the production they're going to use to help clarify.
I see.
Okay. So yeah, basically this thing can, wait, can I start with B's? And you're not seeing it again. What's going on here? And what I typed disappeared. Okay, that's B followed by an S up there. Okay. Basically, looking at the S's that I had, there is no way to start with a B. And so BS will give me something that starts with a B, and then I can put whatever I want after that. Okay, so I can have an A ending it. This B allows me to put in a single B and terminate. The S can be more or not. I think this works. I'm pretty comfortable with it now. Other questions before I move forward? New notation. Shorthand. We usually write it this way. S goes to, and I'm going to put that BS where it belongs, null or A or ABS or just BS. Okay, so I got 4 productions. I rearranged them a little bit there to make more sense. But this, basically, we just list all the productions that start with S. S can go to any one of these substitutions. It's just a nice short way to describe it. And so B now goes to either B or small b, capital B. So B is generating one or more B's, and S is generating combinations of one or more B's with A's between. You can start with an A, you can end with an A. And anytime I go back to S, I guarantee there's at least one B in front of it. So I can't get 2 A's in a row. Ooh, no. The S goes to lambda was bothering me just a little bit here. If there's any point in here where I could get 2 S's, as I did in that other case, then they could go to lambdas and maybe have 2 A's together. I'm not allowing it here. That can't happen, I think. Okay, anyway, let's, so that's an example. Let's go to an example that is a little bit more practical. Give me a second. Okay, a C++ identifier. Okay, what are the rules for an identifier C++? You can mix letters and digits. The first one cannot be a digit. Okay, so I'm going to have S goes to a letter. Followed by T. T goes to a letter T or a digit T or nothing. Is it really that easy? 0 or more of them. Okay. So letter goes to A or B or C or ... Okay, we'd have to really write that out. You're not allowed to do ... dots in real life. Okay, the grammar has to be complete. But for the sake of lecture, or Z. And digit goes to, oh, also or underscore. C++ allows an underscore as a letter. Digit goes to 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. Okay, so basically, T, do I have a mouse? I do have a mouse. Can you see my mouse? Waving my mouse around here. Yes, okay.
Yes.
All right, so T produces any combination of 0 or more letters or digits. Okay, you can get a letter followed by more T, you can get a digit followed by more T, or you can just make the T go away. So T goes to lambda, you get nothing. You can put out a letter and then stop with the next T. You can put out a digit and then stop, or you can put out a letter and then another letter or digit. So T is producing pretty much any combinations of letters and digits. And I am including the underscore as a letter. Okay. That's sort of hard to see there. The underscore character. It looks sort of like it's a hat on that or symbol down there. Okay.
Why do we need the underscore symbol again?
Because that's the way C++ language defines it.
Okay.
I'm shooting for a description of C++ identifiers. And you're allowed to put underscores in C++. Oh, by the way, my letters would also have to include or capital A or capital B, etc. Just remember that. I forgot the capitals here. Okay. Now that's going to get a little confusing. Because now I'm going to have S, T, L, and D here. So I would have to now say, okay, let's mark these as labels, non-terminals. Okay, that's getting horrible. Let me just rewrite this thing. There's got to be a way to delete the whole thing. Yes. Okay, now that I know where I'm going, we'll try again. S goes to a letter, and usually we'd use words at this point. Followed by T. T goes to a letter T or a digit T. Letter goes to A or B or C or C ... or Z or the underscore character. That's more visible now. And digit goes to 0 or 1 or 2 or 3 out to 9. A little more readable. Okay, so again, basically the T, if I was to leave the S off and say my start symbol is T, which is legal, you can identify anything as a start symbol. If I left S off, T is going to give me every possible combination of I have an infinite loop there, or lambda. I could never get rid of it. You got to have some way of getting rid of the T. Okay, so this T is going to produce letter or digit and another T, letter or digit, letter or digit, letter or digit, and eventually make the T go away. The L ends into an atomic terminal. The D turns into a terminal. And so it's only the T that keeps propagating forward and tacking these things together. This produces basically all strings of letters and digits. S says, okay, give me a letter first, and then all strings of letters and digits. And so that's going to produce what I'm after for a C++ identifier. Okay, if we were to sort of characterize, T is all strings of 0 or more letters, digits.
What about keywords? I remember identifiers, you can't like say double or ints, right?
Okay, double is not an identifier. Okay, I'm not defining the keywords of the language here.
Okay.
Yeah, okay, so you're right though. Note, I did not rule out keywords, or the actual word we use is reserved words, such as double. Main isn't technically a reserved word. Return, if, etc. Okay, so I would have to make this a bit more complicated to rule those out. It can be done. It's a lot less pretty. So you're right. I'm that this isn't perfect. We would have to come up with a list of the reserved words and put in horrible things in here to say that can't happen.
Yeah, I can imagine the list be much longer.
Yeah, because you would have to have rules that make sure that certain combinations don't happen. Honestly, I think the way that we would do that is so the compiler is going to describe the overall. In fact, what they're going to do is that they will use this to recognize identifiers, but it will include reserved words. And then once they get that, they'll have a second piece of code in the compiler that says, okay, if it's one of these particular words, it's actually a reserved word rather than a new identifier. The reserved words, I think, do count as identifiers. They're just, yeah, there you go. Okay, I saved myself. The reserved words are identifiers, but they just have special meanings. Those particular words cannot go in certain contexts, which would again make it a little bit harder, but at a higher level. Okay, right now I'm looking at this at what's called the atomic or the terminal level. I'm looking at it one character at a time. Are you with me so far? Just looking at things one character at a time? Everybody say yes.
Yes.
Thank you.
Yes.
That's everybody. You spoke for everybody.
Yes.
Okay, so right now I'm dealing with this at the character level. That's usually referred to as either the what do they call that? This is called the lexical level. Basically, you're going to have one set of definitions, which is going to go and pull out identifiers. It would also recognize, so an identifier is one valid lexical item. Another valid lexical item is a left parenthesis, a right parenthesis, a semicolon. The equal symbol is a valid identifier. The less than symbol is a valid, not identifier, lexical symbol. The less than equals with no space between them is a different valid lexical symbol. And so you list all of the different things that you would see in a language, including identifiers and all the individual syntactical parts. That's round one. Okay, from that you have a description of your program that says, okay, I have an identifier, I have this, I have that, where you have the various syntax elements. And then you go through a similar process. It's recursive one, more recursive than this, which then looks for certain orders. Okay, I've got to have, if there's an if, it must be followed by a parentheses. That must be followed by an expression. What is an expression? It is a term plus a term, or a term times a term, or a term star a term. There's a bunch of combinations there. Actually, term is at the multiplicative level. They call it something else where addition is factored in, because that's at a different level of priority. Okay, that's a good place to stop. We'll sort of continue, and I'll talk a little bit more about this when we come back in about 20 minutes. I'm gonna let my pad rest a little. And that's interesting. I shut my pad off and this still appears. Do I care? Should I stop the share? I'm going to stop the share. I don't know why, but I am. Okay, so see you in about 20 minutes, and I'm going to shut off my microphone. Sorry about that. I was muted. Hopefully I'm not muted now. Okay. I am so paranoid. Somebody give me a yes.
Yes.
Okay, we're good. All right, so grammars. So just to give you an idea of where this would go. Just a very vague idea. I might have something like program. That would be my start symbol. Goes to, now throwing out 99% of C++. Okay, you got a collection of functions. Let's ignore even the fact that main has to be one of them. Okay, so program would be a list of functions. Function list. Okay, function list. Goes to, okay, you got to have at least one. So I'll say function or function function list. Function goes to, and then you go on there. Sooner or later, the function, you would have a function header. You know what? Let's go ahead and fill it up just a little bit more. Function header. Followed by a function body. Okay, the header is your homework, so I'm not going to expand that. The function body would be a sequence of statements. Okay, we're going to use the same recursive method of generating statement or statement sequence. A sequence is a statement or a statement sequence or no. And so you can generate 0 or more statements for the function body. Let's continue that one just a little bit. Function body goes to a left curly brace followed by statement sequence. Okay. The left and right curly braces are terminals, of course. Statement sequence. Goes to null or statement. I believe followed by statement sequence. Oh, wait, semicolon. Sequence. Okay, I can't read that. Anything else there particularly unreadable? Statement, 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 statement. Okay. So statement sequence is, they can be empty or you can have a single statement followed by a sequence. Again, you've seen this pattern over and over again. Function list, I generate a list there. The function list, I ended with function instead of null. So you end up with at least one. If you end up with null, then you allow the possibility of 0 of them. Otherwise, you have a statement followed by a semicolon, and then you can add another sequence on the end of that. Statement, just verbally now. Statement would go to an if case and an assignment case and a while case and a do case and a switch case. And so you would have, like one of them might, oh shoot, stuff is getting in my way, this control panel thing. Okay. So the statement would have the different patterns for the different ifs. It might have if left paren, if left paren, those are terminals. And then you would have a non-terminal for what goes inside of an if. Boolean expression. Or maybe just expression, but let's say Boolean expression. Then somewhere, and then you have a right paren, and then you have another statement. Okay, so one statement is if, left paren, expression, right paren, statement. And I already took care of the semicolons. So you would do that. Statement would go to that. It would go to a while to do. You give all the different pieces. Ultimately, you're going to get down to identifiers. And that's where this would kick in. Although I would use words like, instead of S, I would use the word identifier, because this produces identifiers. It would be part of this system. And that's the entire way of defining a language like C++. There's more to it than just a list of functions, and there's a lot of other, a few other options you can do for functions, but that basically kind of covers it. Variable declarations would have to fit in there somewhere. In C, variable declarations have to happen at the beginning of a statement sequence. So a statement sequence would be variable declarations followed by statement list or something. So you get all the declarations first and all the statements second. In C++, they can be intermixed. So statement sequence, here I have statement. Actually, it would be statement or declaration if you're creating a variable at that point. And it just goes on and on and on. And you end up producing these descriptions. So the earliest languages, Fortran, Basic, COBOL, they didn't do this stuff. They just kind of, like I said, they didn't have all this complexity of statement sequences and functions and prototypes and parameter lists. None of that was in those languages. It was a very simple structure. And so even though they had this concept available at that time, I don't think they were using it really to do their compilers too much. They might have. I find it doubtful. But as we move on here, it becomes more and more necessary to describe these languages. As the compiler is reading the characters of your file, it is matching them against these productions. Basically, you notice that when I was doing my derivations on the previous pages, I mentioned that I was always doing the derivation on the leftmost non-terminal at each point. We have certain rules as to certain formats of productions that are and are not cool. And when you do that, it ends up being pretty easy as you're reading characters of your program to be generating the leftmost production sequence of the grammar. And if at any point you hit a character which does not properly generate any production sequence, you got a compiler error. If you can continually generate production sequences that work until you hit the final end of the program, then you match the grammar and you have this full grammar production of the program. You know the structure, okay, this has got 5 functions, this function has 3 statements, that statement is an if, et cetera, et cetera, et cetera. And it's that information that allows the compiler then to emit the appropriate assembly for each of those pieces. And again, that's why in the homework you just turned into me, each individual statement, a function call, an assignment, whatever, you have a fixed piece of assembly pretty much that goes in for that. And you just follow that rule. We now have what are called optimizing compilers, which will look at multiple pieces of code more intelligently and look for places where bits can be left out or improved upon or whatever. Not necessary, and we certainly didn't have those originally. So this is how, for many years, we produced compilers. We generate the description, and this description actually leads to code that recognizes from it. There's a process there you'll be looking at in the upper division class. What we have today is something even more cool, actually. It's called a meta compiler. There's a slightly stricter form of this notation. Slightly stricter, it's called BNF or Bacchus-Neuer form. What the heck? I think when my pad goes into screensaver, it loses the share. That's interesting. Okay, so we use this to produce the compiler code in the past. What we actually do now is we have what's called a meta compiler. We take this and write it in Bacchus-Neuer form, a slightly more rigid form of the same idea. And basically, this meta compiler can read the description, and then it can compile that language. Along with the description, you provide little bits for each of these individual things. When this is seen, emit this assembly. When this is seen, emit this assembly. And so you have this Bacchus-Neuer form description, which is basically a grammar. You have these little bits of assembly that are tied to each one. And this metacompiler can compile this language. I want to compile a different language. I just generate this description of that language in this special format and feed that into the compiler, into the metacompiler. So the metacompiler has two inputs. One is the description of the language that you want it to compile, and the other is the program in that language that you want it to compile. And I guess a third one would be the tagged bits of emitted code for each piece, if you don't consider that the same. So this is the way we do compilers now. Granted, if we create a new language, we might try it as an experiment with a metacompiler just to see how we like the language, play with it a little bit. Ultimately, when they decide they like the language, they've played with it, changed it around a little bit, they would go back and take the original grammar and produce a compiler directly that is dedicated to that language, because it's going to allow them to optimize a little bit more, to make a much more efficient compiler, et cetera, et cetera. These are some things that you do. When I went through undergraduate, we had a senior level project class. We had 5 senior level project classes, and you were required to take 2 of them to graduate. I think I took 4 of them. One of them just totally revolted me, the topic. And so I didn't go there. But one of those was about language stuff, compiler stuff. And basically the senior level, your entire semester was write a compiler for this language. The teacher gave us a simple definition of a simple language that didn't really exist. And we were to write something to compile it and so we could actually run programs in this little language. Today, if you take that same class, it's very likely that they will say, translate this into Bacchus-Neuer form and then use a metacompiler to produce a compiler for this. Unix has a command or a program called YACC, Y-A-C-C. It stands for yet another compiler. And so it is a compiler that compiles compilers. I kind of lied. The compiler, I don't think it actually, you don't give it the Bacchus-Neuer form and a program and it compiles that. You give it the Bacchus-Neuer form and it produces a compiler for that language, I think is the way it works. Because compiler, it sounds like it's compiling a compiler. So that tool is available. My wife, when she went through undergraduate, she had a compiler class where they were required to use YACC to produce a compiler. It was a fiasco because the teacher didn't understand how to use it. One of the reasons that I have solutions to the homeworks, programming assignments, I give you a gold program. I always do the homework before I give it to you. And the reason for that is to work out the bugs, make sure there isn't something in my idea of the program that you can't do or would be too difficult for you. And this teacher assigned using this YAC program to produce a compiler, having never tried it himself. And he had no idea of the underlying issues that had to be dealt with. It was a horrible, horrible mess. But anyway, so that's kind of where all this stuff is going. It is part of the tools used to produce a compiler. Now actually, this stuff, we don't usually take this down to the identifier level. That's further than this technique would actually go. The technique that is used at the lower level, remember I mentioned what I call the lexical level. Basically, you're reading a character at a time and you're producing what are called lexical objects. An identifier is a single lexical object, the whole thing. And a left paren is a lexical object all by itself. The word if is a lexical object all by itself. It's not treated as an identifier, it's treated as a specially recognized word. And we have a different tool which does the first round of reading your C++ file character by character and producing these lexical objects. So the low-level grunt work is done using that tool. And then the high-level syntax work is done using this tool. In this example, I'm pretending that the low level doesn't exist. And that makes this kind of painful if you were to really try to finish it. Questions to that point? Okay, so I already jumped the gun and basically told you, by the way, if you haven't said yes yet in the chat room, if you showed up really late or something, throw in a yes or a hello or something so that I know that you're present. So the homework assignment, looking at this thing, basically somewhere in here I have function equals function header followed by function body. Your homework is to produce function header. I called it prototype because the header without a body is just a prototype. And so basically what do you have? You have a type, a function name, a left paren, eventually a right paren, and in the middle you have a list of 0 or more parameters, which are each a type and a thing. So you just need to write the syntax for that. You can use this for identifier because we are going to make it all the way down to the bottom level here. It's the only thing is though, this S changes to I. And so anywhere in your homework, when you need an identifier, which is for the function name and the variable name, the parameter names, you just stick an I in there. And this kicks in and produces that where it's needed. Int, float, char, the only three types that I expect you to handle. You just stick those in directly in code here as terminal character sequences. And so it's going to generate those systems. I want to now look at the other level that is normally used at this lower level like this. So let's move to that. So this is called a grammar, generally used to describe the higher syntax level of your program. When you get down to the individual characters, we really want to kind of do something else to bring those together into logical pieces like reserved words and identifiers and type names, things like that. So let's look at this lower level now. This is called a finite state machine. Finite state automaton. Automaton or machine. Both names are pretty common, and sometimes just SM for state machine. Sometimes I use that. Rarer, more rare. Basically, I think the book uses finite state machine. I'd have to go check it to be absolutely sure. Do I have it in my notes which one they use? I have FSM, Finite State Machine, in my notes. So finite simply says that this machine only has a certain number of states. The word state here, in the general sense, I could ask you, what is the state of your health? Okay, it's basically, you know, we have a certain number of variables that describe your health: heart rate, maybe weight, maybe metabolic rate, maybe breathing rate, blood pressure. And if you took all of these and filled in values for them and gave me this list of information, that would be kind of a snapshot of the state at that moment of your health. Okay, the state of the country today. We're all getting sick. You know, the president gives the State of the Union address. Same idea. So a state machine is that same idea, the same meaning of the word, but basically what we have is a bunch of states. Okay, so if I was to describe my wakefulness state, there are two of them. I'm awake or I'm not. I'm asleep. Okay, our finite state machine is going to have a state for every possible configuration of the calculation that I want to perform. Okay, the calculation I want to perform is to recognize some very low level, like an identifier. This would be good for that. We may make the state machine for an identifier here, just to compare. Okay, between states, we have transitions. And each transition has a label. Let's jump right in and do an example and see how all this kind of fits together. I want to recognize, let's do that one with the ABBBAs things. Example. This is much easier than the grammar. Example. All words not containing a pair of A's together anywhere in them. Okay, so we have a state. And just a sort of an arrow pointing into it from nowhere. That indicates start state. Okay, if that is not coming from another state, that just says this is my starting state, just like we identified the starting non-terminal in the other system. Okay, so now what I want to do is, as I'm reading each letter, and my alphabet here is A and B, so that's all I need to deal with. As I read each letter, I transition from this state to another state depending on the letter. So if I read an A, I'm going to go to this state, and if I read a B, I'm going to go to this state. Okay. Now we have an indication of a start state. We also want an indication of a final or accepting state. Okay, so let me sort of put off to the side here. Final, final or accepting state. Now basically, the way this finite state machine works is you start in the start state, it starts there, and it moves around from state to state. Okay, in terms of computation modeling, this would be, I've got a program and it's got an X that has some value, that is the current state. If the program does something and says X equals X plus 5, I would move to the state that represents that new value of X. Okay, we would have a state. In a real machine, we would have a separate state for every single possible value of every single possible variable in all combinations. In other words, a ridiculously huge number. We don't use this for modeling computers as a general rule. Strangely enough, we do come back down to this simple model when we want to learn about the limits of computability, because the idea of a massive machine is not daunting to a theorist. We basically say the rules are simple. We can analyze what these rules, how these rules will allow what this machine is capable of doing. It doesn't matter how big it is. The rules are simple, and that's all that matters. So this very simple model ends up helping us learn about computation quite a bit. But in reality, you would never, in practice, use this to represent a computer. RAM memory on a computer, how many bytes do you have? A terabyte, okay? That is 8 terabits, okay? You would have to have a different state for each combination of memory. That is 2 to the 8 trillion power. Okay, that's just kind of way out there. Okay, that's probably more than the number of square centimeters in the known universe. And that's a pretty big number. More than the number of electrons in the known universe, whatever. That kind of scale is just not practical. We're going to look at things that are practical, small things, like words that fit this pattern. Okay, so the machine starts in start state. That's identified. You have one arrow going into one state. In every state, you will have a transition for every letter of your alphabet. Now, I've only got A and B, so I got 2 transitions coming out of this thing. In every state, you will have a transition leaving it. And so the way the machine works is you start here, you look at your input. Okay. If the first letter of the input is an A, you go this way. If the first letter of the input is a B, you go that way. And then you again look at the input and decide where to go next. Okay, now, do I accept in this language a single A? Is that a valid word in my language? I believe it is. So this one needs to be an accepting state. What the machine is going to do is it is going to follow this rule. There will always be a path leaving every state for A and for B. You start at the beginning, you start reading your string. Every single character of the string you're reading is a state transition. And when you run out of input, whatever state you're in, if it's an accepting state, yes, I accept that word. It is in the language. If you end up in a non-accepting state, like the start state is non-accepting, my language, oh wait, that's an accepting state too. Because the null string does not contain two A's. So that would be in the language. Okay, so null string, we accept it. If I see a single A and I'm done, we accept it. If I see a single B, we accept it. This is a very accepting machine. The only deal is, okay, let's look at the A state. This state cannot be an accepting state. I saw 2 A's in a row. It's the only way I got there. And so if I get to this state, I can never accept no matter what input follows, ever. Never, ever accept it. And so the state up here has to be a non-accept, and anything that follows it is non-accept. What I'm going to do here is make a path for A and a path for B. In other words, once you get into there, there's no getting out. So if I had, okay, I haven't filled in other B's yet, but if I had AA and other letters following, I would just keep following the transitions here back to the same state. And whenever I run out of input, I'm in a non-accept state. That is often called a sink. Because there's no way out. This is a non-accepting sink. I could also have an accepting sink. Okay, if there's some criteria by which, like if I want all words containing AA, then these would be non-accepting, and that would be an accepting state. Once you've seen 2 A's, doesn't matter what else you see, we're good to go. I accept the word no matter what else is there if I wanted the yes containing. Okay, so let's look at the other possibilities here. I got a B. Is that an accepting state? Yeah, actually, I'm going to back off of this one. I believe I can. Okay, that was wrong. S-I-N-K. I want to erase that other arrow. And I'll go to that state, B. If I see a B, I'm good. If I see an A followed by a B, I'm good. I can have all the B's I want. If I see more B's, I'm still good. The only deal is if I see an A, I'm on notice. Okay, I will still accept. But if I see another A, I'm going to go to that non-acceptance thing. Notice every state now has 2 exits from it. It's not the case that every state has 2 arrows coming into it. Well, actually, this one does seem to be that case. That's not necessarily true. Okay, every state has 2 branches leaving it for each of the letters in my alphabet. The number of letters coming in. Hey, I can throw a state out here and have nothing going to it. Not useful, but I could technically call it a part of my machine. I could have one state that a whole bunch of states have things going to it. That's okay. So what does this thing do? Anytime I see an A, if I'm here and I see an A, I go to there. If I'm here and I see an A, I go to there. Okay, if I'm here and I see an A, I've already lost because I saw 2 A's in a row. This state basically means, my semantic here is if I'm in this state, I have seen 1 A, and I got to watch out for the second one. A second A, I go into the non-accept sync. If I stop there, I'm okay. If I see a B, I go back to here. I'm off notice now. I can see another A, I'm okay. So this state, I can make it simpler. I think that I can combine the start state and the B's. Let's try that. An alternate version of this. Start state B, A, that's an A, believe it or not. That's okay. A second A is a non-accept sync. If I see a B, I can go back to there. A little bit simpler. So basically, anytime I'm here, I'm good to go. 0 or more characters. I have never seen 2 A's in a row. If I see a B, I can see all the B's I want. I'm fine with that. If I do ever see an A, I'm still accepting, but a second A, and I give up forever. If I see an A and I stop there, I'm good. If I see an A and I see another B, I'm still good. Basically, this state says, I have not seen an A in recent history. This state says, I have just seen an A. I'm watching out for that second one. Each of these states has a meaning. Okay. This one is I've seen 0 A's in a row in recent history. I've seen 1 A in a row in recent history. I've seen 2 A's in a row, not only in recent history, but at that point, I give up on recent history and just say, okay, I give up. Let me give you another one. Okay, variation. Not end with AA. I'll take any word as long as it doesn't end with AA. Okay, that's not going to work. I have to go to another page. I didn't realize I was so near the bottom. Okay, got a little extra line that I used for separating. Okay, so if I want to not end with AA, the thing is I'm still looking for AA. I just have different criteria for accepting. And so basically I'm going to start out with start state. That doesn't end with AA, so that's good. If I see an A followed by an A, that is a non-accept state. That one's okay. That much is the same. I'm still looking for that AA. It's my primary consideration. However, the rest of this changes a bit. Okay, if as long as I see B's, I'm good. Hasn't ended in AA. If I stop in the middle state, I'm okay there. I've seen 1A, we haven't ended with AA because it was preceded by B's probably. So 1A is okay. If I'm here and I see a B, I go back to the state again. Again, I'm counting A's here. Okay, I've seen 0 A's, recent, 1A, recent, 2 A's exactly, recent. Actually, not exactly. Okay, so now let's look at these other missing edges. Okay, I've got A and B here. I'm good with that. If I have 0 A's and I see a B, I still got 0 A's. If I've got 1, okay, so 0 A's and a B. 0 A's and I see an A. Okay, I got 1A. 1A. If I've seen 1A and I see a B, okay, my recent history doesn't have an A in it. The B has erased that one. It's no longer an issue. So I go back to 0 A's. If I'm at 1A and I see another A, I go to the state that says I've seen 2 A's recently. Okay. If I see a B, I have no A's recent. Ah, what happened? If I see an A, okay, so if I see, for example, an input string of A, okay, first A, okay, no A's, I'm here. First A, I'm there. Second A, I'm here, not accepting anymore because my word ends with AA. If I see a third A, well, there's still 2 A's at the end, which is not allowed. Okay, so I'll not accept that. But I could see A, B. Okay, I can see all these A's and I'm not accepting as long as I see more A's. But the second I see a B, oh, I'm okay again. I'm not ending with 2 A's. Okay, so this sequence is looking for 2 A's, and that is the one case. If I stop here, my word ended with 2 A's. If I stop anywhere else, it ended either with a B or nothing or a single A, preceded possibly by B's. Okay, so this is our finite state machine idea. Questions? Something kind of interesting. The finite state machine and the grammar are capable of describing exactly the same collection of languages. There are languages that these cannot describe. Certain definitions these will never handle. For example, if I have a bunch of B's, a single A, and a bunch of B's after it, I can recognize that, but I cannot specify only words where the number of B's on the left and the number of B's on the right are equal to each other. If I have 5 B's to the left and 5 B's to the right of that center A, they have to match. If I have 4 B's on the left and 5 B's on the right, that is not in the language. That one, this machine cannot measure. Think about it for a minute. I'm using states to count A's. If I allow any word and I want the equal amount of A's, I have to count the A's with states. And then for any number of okay, actually I would want to count the B's until I see an A. And then I would want to count down the number of B's that follow it, whichever way I'm doing it. I need enough states to count them. And with an infinite language, no matter how many states I have, finite state machine, no matter how many states I have, as soon as I get a word with more than that A's on the left and right, it's going to fail. It can't count it properly. So that language, which is a perfectly reasonable language to discuss as a language, is not recognizable by this system. That same language is not generatable. Wait a minute. I can generate that language with a context-free grammar. We would write that as A to the N, B, A to the N. Equal number of A's on either side of the B. Okay. The finite state automaton, impossible. the grammar, it's actually pretty easy. I go S goes to ASA or B. That's it. Okay, basically, as long as I use this production, it's going to throw an A off both sides. They will continue to match forever. I can throw as many as I want off. And I will finally finish with B in the center of those two groups. It allows you to go straight to B and have that N also be 0. It allows any combination. So the grammars that we're looking at are a little bit more capable of expression than the automatons. If we added a little tweak to the automaton, it would be equivalent to the grammar. We're not going to do that. Okay, we're going to stick with a finite state automaton. But we do know how to beef this model up ever so slightly, and they will be exactly equivalent to each other. That's a known thing. It's easy to do. A cool thing, if I want to generate a grammar and I'm having a hard time like I was having before with that language, I was having, I couldn't quite get it right at first. A lot of times it's easier to draw the automaton for it because it's sort of a very plotting, counting kind of a thing. And if I can generate this, we have an algorithm, a program. I wrote it once. It took me a few days, but we have a program that will take a description of a finite state machine and produce the grammar from it. That's a thing. We can do that.
Can we get that program?
No, you can't have it. I wrote that thing 1,000 years ago, dude. I don't even know if it was probably in C, not C++. There's a time when I was teaching at Cal State Fullerton and I taught the upper division class in language theory. And we did this. We spent several weeks producing automaton. We spent several weeks producing finite state machines, and we spent several weeks producing a third notational system. And then we looked at the techniques. We just, talked about the techniques of converting between the three, which proves if you can do that, that they're all equivalent in capability. And again, you have to pump this one up just a little bit to get that equivalence. But in order to teach in that class and give homework assignments that I needed to be able to grade and stuff, I wrote that program to serve me. I have a bunch of programs for 129, this class, that served me. For example, when you did that thing where you took your name, your initials, and calculated the various answers, I have a little app that does it. I'll show you. Okay, I need to stop this share. I need to share my screen. I don't want to share the iPad. What happened? Okay, let's try that again. Share screen. Okay, so if I go to my 129 folder, common, name base, I'm embarrassed to say I wrote this in Visual Basic because at the time I did not have a reasonable Windows level C++ compiler. So the language sucks, but at least I got this. So basically my name is JHH, or I think in my example I said JXH. Okay, it gives me the actual letter positions in case I want to check that against your work. It gives me the decimal, the octal, and the binary for it. The cool thing is, let's say that in taking your name and calculating the decimal, you got it wrong. Okay, maybe for the J you got 8 instead of 9. Okay, I can go down here and so your calculation went to 668 8. And the rest of your work is based upon that. Well, I can just go boop. I got the difference. Actually, I said the J was off. That would be this one turns into something else. What I would do is if you got the wrong thing for J, I would just put what comes for J, H, I. And that would give me with the other thing, and it calculates that. Basically, it allows me to check your work easily. As I'm grading that homework, I have this present. And generally speaking, all I do is I just type this in. JHH, okay, there's mine. It highlights automatically So if your name is Alfred E. Newman, A-E-N, there it is. Notice it's just E-N because the A is 0. If it's a leading A, it really doesn't count. Makes it very easy to grade that homework. Without this, it would be a nightmare. People, the reason I'm showing you this is because you're in a program to learn to be a programmer, among other things, computer scientist in general. You have to think of, if I have a tedious job to do, I need to write a program to do it. Okay, you need to have that mindset. I will solve my problems with programs rather than doing it myself in tedious activities. I just recently, okay, going back to my pad now. Okay, just go away. Closing this for a moment. I just recently started playing a game. It's kind of like Sudoku, kind of. Where's the practice level? So what this tells you is there's a group of 3 consecutive, and there is a 1 that is not consecutive with a 3. There's a 1, at least 1 space, a 6, at least 1 space, a 1. Doesn't that sound kind of like the words we were describing? There's at least, you know, there are a certain number of just X's, or whatever you want to call them, and they're in groups defined by this. This one is all solid. Okay, you have a choice down here of choosing either solid or not solid. So with solid selected, I say, okay, all 10 of those are solid. All 10 of these are solid. 8 of them, I'm not too sure. Okay, there's 8 together. Usually what I would do here is I would say, okay, those 7 I'm sure of, or, okay, I got lucky. It should have been, let's do the 7 down here. I don't do 7 across, that's stupid. I do, that many, okay? It could be 7 on the left. It could be 7 on the right. It could be 1 here and 2 over there. I don't know. And so through various, adding more information and figuring things out, you eventually try to figure out the whole thing. About 2 nights ago, I was awake for a few hours in the middle of the night saying to myself, I'm going to write a program to solve this. That's the way I think. Okay. I enjoy playing the game. I will always play it, without the program's help. But like last night, they have these challenges that are timed. And last night, and it goes several days. And basically last night, I had too much work to do. It's why I didn't get your test graded. I got stuff kind of piled on me suddenly. And so basically, I didn't even have time to play my game. And I didn't win this challenge. And I'm really ticked off about that. So I'm going to write a program to solve these things. You give it as input these vectors of hints, and it figures out a solution that works. That's easy. It's a technique in programming called backtracking. Piece of cake. The problem is this is a medium level, not even the hard one. How many boxes are here? 1, 2, 3, 4, 5, 10 by 10. That's 100 boxes. Okay, each one can either be a solid or a not solid. Okay, if I choose and put an X there, okay, there's not a solid there. I got lucky, I didn't fail. So now that I have that, by the way, I know that 9 are those 9. So anyway, there's 100 boxes here. Each one can be 0 or 1. How many different combinations are there? 2 to the 100th power. Again, a completely astronomical set of possibilities. So I cannot just write a basic backtracking program that generates all combinations of 1s and 0s. The sun would burn out long before this thing finished solving a problem at this level. And there are harder levels later, 15 by 15s. So basically what I spent my time during that night doing was thinking about how can I make the program not do so much work? Instead of placing all combinations of 1s and 0s, I know there are groups, 2s, 6s. Can I adjust a program to say, you know what, only place them in groups, okay? 2, I can't do much with that. Okay, I can put the 2 here. The next step would be to put the 2 here, then the 2 here, then the 2 here, then the 2 here. Okay, I would not put 1 here and then 1 there, 1 here, 1 there, 1 here, 1 there. Those are not solutions. So by changing the program, making it a little bit more complicated and keeping the groups together, I actually think that alone would take it down to something that the machine could calculate within a reasonable amount of time. It's still an exponential potential nightmare. But I thought about it some more and I came up with a couple of very simple primitive calculations. Very easy to calculate, and using those two as a decision as to whether or not to attempt placing a value there, I think this thing will actually solve in microseconds. Okay. Programmer stuff. Finish the game now, I'm intrigued. It's a fun game. It really is. Okay. I've got vertical 10s. Those are easy. Oops. What's going on? Okay. I've got a 9 to the right of that, which means I don't know for this 9 whether it's the top 9 or the bottom 9. I don't know. One of these two is solid, the other is not. So the way I do that to be safe, because you only get to miss twice or 3 times, is I go with 8 of them, and I'll look for other hints to help me figure out which one of those it is. Okay, 10 down here. Boom. Now I know that's got to be a 0. I think of it as 1 and 0. Okay, so I can check that as 0. The worst part of this game is not the logic and the math. I've got a bunch of little mathematical formulas. My wife and I have both developed them independently of each other, and we compared notes and had basically the same formulas. But the worst thing about this game is I think that if I click here, I get the solid block, and if I click here, I get this other thing. It's not the way the interface works. It doesn't matter. I'm going to click on the left-hand side, which should stay there in my mind, and it switches anywhere along here. If you click on it, it simply toggles that. And so I am constantly doing operator error of thinking I set it one way, clicking, and it wasn't the way I thought I set it, and I immediately get an error. I knew what the answer was, and it just was the wrong side. Really annoying. Okay, this 8, I know it's rooted here, so I can just go up 8 from there. And now I know the 2 above are safe. You don't have to mark the safes, but it's just helpful to keep track. Okay, 6, there are 5 there. So there is at most 1 here to get to 6. And if there is 1 there, I can't put the 1 here. Well, right there, it tells me the 1 needs to be the left of the 6. So that's got to be a 1. It's the only option here. So I will go for a 1 there. The next one's got to be an empty. And now that I know that the 6 starts here, there are 5. There's 1 more. It's the only choice. And the other 1 is not a part of the 6 group. I only have 1 place to put it. This picture ends up, a lot of their pictures are fairly symmetric, not always. Let's finish this up. Okay, I got a 3 and a 2. Well, there's a 3 here. So I know nothing there is useful. I can't put anything up there because the 3 is already accounted for. And the 2, it's got to be this one here. And mark the ones that I know. 8 is rooted on the bottom, so just fill that in. Once you've filled in all the pluses, they then color it and give you these cute little names of the pictures. It's amazing. They have hundreds of these puzzles, maybe thousands. And every single one of them, they have some name of what the picture is of. It's a very low resolution picture, obviously. It's a fun game. But like I said, as a programmer, I do enjoy playing it. But I'm thinking about how can I write a program to solve this? And the practical application of that was I ran into time trouble. The last challenge ended midnight last night, and I only had a few difficult ones to go. Another 2 or 3 hours and I would have completed it, but I didn't have that time. If I had the program sit in there, I could have, well, let's cheat on these. So arguably practical. Okay, let's put that away. Anyway, that's what I like doing. I like writing. From the first day of programming, I've always been interested in taking puzzles and writing games writing programs to solve them. I really enjoy doing that. And in the case of a puzzle like this one, where the basic brute force complexity is way too high, you have to start figuring out how can I be smart and reduce the number of things it has to try to where it can calculate within a reasonable amount of time. That's called pruning. You'll talk about these techniques a little bit in the data structures class if you haven't already had it. You talk about it a lot more in the upper division algorithms class. If you take artificial intelligence classes, you'll talk about it a lot, because artificial intelligence is basically trying to solve really, really hard problems within a reasonable amount of time, which means that you can almost never apply brute force to them. You have to come up with intelligent ways to address solutions. All right, let's move on to stuff we're talking about for this class again. Going back to the notes program. Okay. What happened? Going back to the notes program. Okay. Close, open that one again. All right. So these are my finite state machines. There's nothing else to them. There are tricks and techniques, okay? Now this one is not a sink. Going back to the previous page, that one is a sink. Once you get in, you can't get out. I can have a non-accepting sink or an accepting sink. If there's some criteria, like maybe I want the language contains at least one A. Okay, let's do that one. So where's my stylus? Okay. Contains at least one A. Okay, we got a start state. Okay, is the empty word acceptable? No, doesn't have an A in it. So I start out not useful. If I see an A, I'm good. That's an accept state. And anything after this, I'm good. So I have an accepting sink. The only other edge missing is the B coming out of here. And as long as I see a B, I'm not accepting yet. I'm waiting for that A. A very simple machine for that test. We use these machines for a lot of things in practice. We actually build them out of circuitry. Your modem that translates data from the internal computer format into something to be transmitted across a network port or a phone line, a DSL line maybe. There's different formats involved there. And your modem device actually uses a finite state machine to translate the data into the other form and to translate it back. It's not a recognition task, but this can be, again, like the program in the grammar, you can tack outputs onto these. We'll be looking at that later. You can tack outputs onto these. And so as it's transitioning states, it's outputting something in addition. We'll be looking at that, I think, next week a little bit. But later on, we're actually going to look at, this is the heart of your computer. Okay, going back to our first week chart of the von Neumann machine, we had the input device and the output device and the memory device and the CPU device. The CPU device, the heart of that, the thing that goes round and round and does stuff, is a finite state machine. And right near the end of the semester, a little short of the end of the semester, we're actually going to look at the circuitry of how the control unit of your computer is designed using this technique. We'll be looking at the circuitry level of this at that point. How can you build this with a circuit? But at that point, we'll be able to do that. So this is, for right now, a recognition system. Let's say I want to recognize some more examples. Word containing A. I
don't think we can see what you're writing.
Okay, thank you. Let's try rebooting the thing. Come back. And I lose the last thing I typed during that time. Contains, to make it a little bit more interesting this time. Give me a second. I want to think of something that will demonstrate some ideas. A, B, A, A. As long as that is somewhere in the word, I'm good to go. Okay, so basically I do this left to right. I have a start state. I'm looking for an A, followed by a B, followed by an A, followed by an A. That's the basic backbone of this chart. Okay, when I get to here, I have an accept state. Now the question is, at each level, where do I go if I see not along this pattern? If I'm at the beginning, I've seen nothing yet, and I see a B, I stay here. Okay, what do these states mean? I've seen one letter that I want. I've seen, okay, this one I've seen nothing useful. I've seen one thing useful. I've seen two of this substring useful. I've seen three of the prefix of this substring useful. This one is I've seen the pattern I'm looking for. Okay, so if I see an A, I go to here. If I see a B, I move on. If I see an A, you could think, well, I need to start over because it's, you know, AA doesn't do anything. But consider the input A, B, A. Okay, the first A is going to get me to here. The second A, I do have the thing I'm looking for here. Okay, I do have it. So if I don't see the B here, I don't give up. I say, you know what? I've still got one useful A here. I stay in that state. Okay, first A looked useful. Second A, this one loses its value, but that one could be the beginning. So I stay out. I've seen one A. Okay, see a B, go to here. If I see another B here, okay, my last two things I've seen are B, B, and I got nothing that's going to lead me into that. I got to start over. Okay, going to the next state. If I see a B here, okay, so that would mean that in recent history, I saw A, B, A, B. And who knows what before that. Okay, if I'm in this state, the last three things I saw were A, B, A. And what happens if I see another B? Basically, this part is useful as the beginning of another possibility. So I take this one back. That's wrong. If I'm here and I've seen A, B, A, and I see a B, I go back to the thing that says, I just saw an A, B. And I start up. So basically, I sort of had this pattern, which is useful for designing a lot of these things, where I'm counting progress towards my goal. And at any point where I don't see my goal, I have to look at the suffix of the things I have seen, including the thing that failed me, and ask, of that suffix, is there anything that qualifies as part of a new possible solution? And if there is, go to the state that would be that point. So I see a B here, I can start over. If I see another A, another B, I'm still good. I've seen an A, B at that point. Okay, so if I say contains this, I have an accepting sink here. If I say contains it. If I did say, on the other hand, let me change color. Okay, instead of contains, I'm going to change it to ends with. Can you see that? Yeah, okay. Okay. The only change, all the rest of this is good. It's just that when I get to here, if I'm here, it accepts because I've just seen that in the recent past of my inputs. But if I see an A here, recent past is A, B, A, A. Okay, so the A would have to go back to, stop that. There, okay. That would be a case of seeing A, B, A, B, A, And then immediately after that, I saw another A. I can use that to look for the sequence again. It's the only part of it that is useful to me. So I go back to here. If I see a B here, my recent history is A, B. And I can, oh, wait, no, A, B. And I can use that for this part up here. So a B actually would go, oh, it's ABAA, sorry. I was looking at the string up here and thinking that was my goal. ABAA, if I see a B there, I can go back to the AB spot. Okay, so it's all the same for the first three states leaving them. For the final state, if it contains ABAA, you just stay there. If it ends with ABAA, then I see an, oops, label it A. I would have to leave the except to go back to here and start looking for BAA again. If I'm in here and I see a B, I can use the A that got me here, B, and start looking for another AA. So this counting thing, kind of useful. We can extend that even further, that idea. Let's say I want an even number of A's. And I can do any of the four combinations here. Even A's, even B's, even A's, odd B's, whatever. And odd B's. Okay, I need to keep track of two separate criteria. And I'm going to use this idea for each of them. I'm going to go across to keep track of A's, even, odd. And I'm going to go vertically to keep track of the B's. So I have four states. This vertical direction is my A, and I'll say even, odd. And horizontally, B, and I'm doing even, odd. So if I am in this state, I've got something in my way here again. If I'm in this state, I would only be there if my recent, or if the total A's I've seen so far is even, and the total B's I've seen so far is even A's, even B's. If I have odd A's and even B's, it would be odd A, even B. I've got my four combinations here. Now, when I start, 0 A's, 0 B's, that's even. So that's my start state. Okay. From any state, if I see an A, I travel vertically from between even and odd. If I see a B, I travel horizontally between even and odd. So it's going to look like this. AA, AA, B, 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 B. Okay, A's always travel vertically, going back and forth between the even odd situation. Every time you see an A, it changes the even odd count of the A's. Every time I see a B, it changes the even odd count of the B's. I'm not counting them. I'm not looking for 1, 2, 3, 4, 5, 6 because a finite machine is going to run out of states. But if all I care about is the even odd issue, I can keep track of that perfectly fine. Okay, now even A's, odd B's. That is A's even, this level, B's odd over here. That's the state that I want to be my acceptor. Let's do one more. I think I will try to do it. I'm sitting here trying to figure out how to draw a line with my I don't know if I can fit it here or not. Let's try it. I want even A's. Exactly 3 B's. They don't have to be consecutive. Okay, the word has to have exactly 3 B's in it and an even number of A's. Okay, I'm going to use the vertical to keep track of the A's again. I'm going to use the horizontal to count to 3. So I have my A, even, odd, and I have, this is going to be B. I've seen 0 of them. I've seen 1. I've seen 2. I've seen 3, and I've seen more than 3. Okay. I'm not writing that last one for a moment here. Okay. These states will keep track. I will always go vertically. If I'm here, I'll go straight up. Okay. I've seen 1 B. I see an A. The A changes. If I've seen 2 B's and I see an A, the A changes. Okay. I call this my dimensional approach. I made up that name. Basically, I use one dimension of my chart for each criteria. If I have 3 criterias, I got to figure out a way to draw a 3-dimensional object. Real easy if I'm writing a program to do it. It's a little bit harder on paper, but I could do it. Okay, so I count up to 3. 3 B's are these 2. What did I say? Even A's is this one. This is my only except state. I need to fill in the arrows here. A's go up and down. B's go always to the right. Now, if I get to here and I've seen 3 B's, either A combination. Okay. If I see another B, it's a non-accept. That's going to be a sync because I say exactly 3 B's. So once I get up to 3, not acceptable. Once I get to 3, yes. One more, and it's just a no. I don't need a I don't like it, non-accept for B equals greater than 3, and another one, and keep track. I don't need to know if A is even or odd at this point. Okay, I've decided I don't care anymore. So I would, even though I could do this regularly, I'm just going to add A, B, a non-accept sync. Okay, filling in all the other pieces, I have AA at each level of B. Whenever I see a B, I move forward in my count. If I see another B, I'm out of there. Okay, so this thing is gonna be in the accept state. If there's an even number, every time there's an even number of A's, and I've seen exactly 3 B's. Until then, I'm counting B's and I'm keeping track of the what we call a parity on the A's. Okay, up to 3, it matters. After 3, if I get a 4th B at any time, I drop it in the non-accept state after that. You can have multiple non-accept syncs, but there's really no point in it. Okay, so these are our, I need to determine a start state. That would be even A's, because that's 0, and 0 B's. Don't want to forget those guys. How are we doing? Identifiers. My C++ thing. Okay, start, letter. That's just a fancy way of saying A through Z. By the way, it's okay to have a transition and say A, comma, B. It means the same thing as A, B. If you have multiple arrows going from the same place to the same place, you can just draw one arrow and list that. If you have like letters, you could say A dash Z, you know, basic notations to indicate multiple branches are okay. In this case, letter. It's also okay to write not letter. But the thing is, whatever your alphabet is, the total letters, characters you allow, every state has to have an exit for every letter of that alphabet. Okay, now when I'm talking about letters of an alphabet, I'm including whatever characters are in there. So this, in this case, I'm thinking A to Z. Maybe I should write that. A to Z. Okay. So let's maybe not even say letter. Okay, that's accepting once I see a letter, comma, underscore. Once I see that, I'll accept A to Z, comma, underscore, comma, 0 to 9. Okay, what else is there? 0 to 9. Everything. Whatever that is. Okay, when I start, I got nothing. It is not an acceptable identifier. We got to start with a letter. If I see a digit first, it is not a valid identifier. I go into a non-accepting sync where I stay there on all further inputs. If I do see a letter, A through Z or the underscore, okay, I've already got a good variable name, a good identifier, and pretty much anything in this range is still good. If I allowed a bigger, what's the word? Alphabet, like I want to deal with the whole keyboard because this is part of a larger system that is recognizing C++, I would not want to make one of these to recognize C++. But if I was doing something like that, if there were other characters in the alphabet that I'm dealing with, I would have to have the arrows for those other characters. You know, any like if I see in C++, you know, A, B, B, A, 1, 2, 3, that's a valid identifier. If I see a right parenthesis, okay, I would have to have a branch for that if it's allowed. Would that go to a non-accepting sync? That's kind of a weird one. I would go to somewhere that says I've seen a valid identifier, but now I'm starting to look at something else. Okay, if I'm in a context where an identifier is expected, a 0 through 9, or pretty much anything except a letter, actually, is going to go to a non-accepting sync. We've already failed. And that's where the compiler would kick in and say, I don't know what you're doing here. This is not appropriate. If I wrote XYZ main as a prototype to main, XYZ is not a known data type. And so looking for data type, you know, things, it would go down here saying, you know, that's not an int or a char or whatever we know about. Actually, again, it's a two-layered system. If it was all this way, that would be the case. The reality is we use this system to recognize the individual lexical objects, which is identifiers, reserved words, single character syntax things. Okay, it recognizes those and it throws it to the next layer, which is the syntax layer. And that thing looks at, okay, is a parentheses expected here? Is an identifier expected here? And that's using the grammar. So that we sort of have this two-tiered system that does that does a compiler's job. This is better for the low-level pick out words kind of thing, or numeric digits. What would it look like to recognize a number? An integer, literal. Okay, we start out. You can have a digit, and and that's accepting. You can have, and then more digits is okay. I'm not going to deal with, excuse me. Okay, D equals digit. Okay, I'm not going to worry about, okay, and in reality, you know, an integer can only handle 17 digits. Okay, I'm not putting limits on it. But I could also see a minus and then a digit, and we're good to go. After that, you're not seeing what I'm writing. Let's reset. Okay, so an integer literal value in code. When you start looking for an integer literal, a digit is good and more digits is fine. No digits is not an integer literal. If I see a negative sign, digit. Okay, so my alphabet right now is digit, negative sign, and other. And basically any other is a non-accept sync. Okay, I'm looking for an integer literal and I see a letter, A. I'm dead. See a digit, I'm good. See a negative, I'm good. And again, if once you get into here, you see a letter, well, you got your integer literal, now something else is coming in. Okay, if I'm here waiting for an integer literal and I see a letter or something which is not a digit or a minus, I'm going to go into a non-accepting sync. Okay, we're allowed to also use plus, minus, comma, plus. You are allowed to put a plus in front of an integer. It's kind of pointless, but you can. So that would be an integer literal, something built into code. Float is a little bit harder. Okay, you know, what does a float look like? Let's see. I have a sign, which is optional. I have a mantissa, xy dot zw. Or let's not write it that way. Let's write it. I have plus or minus, or nothing. I have a digit, dot, digit. 0 or more on either side of that. And in fact, I think you may be allowed to leave the decimal out. I'm not sure. Not positive. And then we have optionally E plus or minus digit for the exponent of a floating point. Can I make a machine that does that? Okay, I start out with starting with my start. Okay, a plus or a minus, a digit. I allow more digits. Period. I need at least one digit. More digits. Wait, do I need a digit after the period? You know what? The way I have this written right now, I'm requiring one digit to the left of the decimal point. That's not actually required. It gets a little hard though, because if I have 0 digits here, I got to have at least one there. If I have one digit, if I have at least one digit here, I'm allowed 0 there. So how am I going to do that? Okay, let me see. Plus, minus, or nothing. Start, oops. Start. plus minus, digit, more digits, decimal point, okay. Yeah. Oops. Where do I get my plus minus here? I can have a plus minus before the decimal. I can have a plus minus before digits. So what I really kind of want to say here is plus, minus, or nothing. That would be very useful on the early part of this thing. Unfortunately, at this stage of the game, we don't have a nothing. The book has some discussion of non-deterministic machines. I might talk about those next semester or next week or a week later. A non-deterministic machine can have lambda transitions, meaning you're sitting in this state and without even reading input, you can do a state transition on a lambda edge. At that point, you have an ambiguous execution because you're sitting in this state. You could just jump to that state if you felt like it, or you could read a character and jump to that state or to a different state. Up until this point, you're in a state, you have exactly one edge leaving for every letter in the alphabet. There is no ambiguity. The machine will run in a completely fixed process. A non-deterministic machine allows the possibility of, the machine apparently has the ability to make a choice as to which way to go. And the thing is, when I define non-determinism for you, it's basically the machine has an oracle. It will make the right choice if there is a right choice to be made based upon future inputs that haven't happened yet. Sounds like magic. The strange thing is that actually gives us a useful definition. I'm going to get this thing to work, whether it kills me. Okay, literal float value, or float literal. You've lost it again. This is really annoying. Okay, so float literal, or literal float. And again, we basically have the plus minus possibility. We have some digits, we have periods, we have some digits, we have E. That's optional. Followed by at least one digit, and pluses and minuses inside there. Okay. I am going to assume that a decimal is required. However, I can have plus, minus, or digit. Okay, if I see a plus, then I can see a digit, or I can see a dot. If I see this digit down here, if I see plus or minus, that can go here. Okay, this thing can have any number of digits. Eventually, I can see a dot. Now, I'm separating the dots here because this dot has a digit preceding it, at least one. This dot doesn't. This one needs a digit. That one doesn't. Remember, you can't have a floating point which is just period. There's got to be at least one digit on one of the two sides. So that was the problem I was thinking about before. Okay, so if I've on the uppercase, I can have 0 or more digits. And that is an accepting state. I could see E. Okay, going back to the other period, this period down here, I have not yet seen, I didn't see a digit to the left of the period, so I've got to have at least one to the right. Digit. Okay, now I can have more digits there if I want. Okay. There we go. So getting to this first accept state, I can see a sign or not, a sign or a digit. Actually, I could have a period in there too. If I have a period coming out of that first one. I still need to have at least one digit if I just start with a period. So this thing basically says I'm ready for digits. I've handled the previous stuff after the decimal. This one says I'm handling digits before the decimal, and at least one after this decimal because I had some before. I found the rest of the digits. Once I get to the exponent, it's going to look kind of like a short version of what I already have. No decimal this time. So after the decimal, I can have a plus, a minus, or a digit. That's an accept. Plus or minus, I need a digit to get me there. After this, that's pretty much it. There are some characters missing in here. Okay, notation. Shortcut. Leave out paths or transitions. To non-accepting sinks. Okay, if we leave out, I can't read that. Non-accepting. Sinks. Okay, so if we have a finite state machine, technically there must be a branch leaving every state for all possible alphabetic values. If we start leaving transitions out, the rule is if you get to that state and you read a character where there's not a transition, that is a fail. In other words, the machine in any branch that is missing goes to a non-accepting state. Okay, so all of them, you can have one non-accepting state and fill in all the branches if you want. We tend to leave this out. It's not changing the machine in any significant way. It's just saying, you know, hey, if you can't find a branch, the machine will read the rest of the input technically, but it's not going to accept it. Okay. You can have more than one digit on your exponent. I think you can only have about two, but okay. A little bit ugly here. I could probably, if I sat down and thought about it for a minute, I could rearrange these states a little bit to make it a little bit more clear what's going on. The real issue is just that period. You can have digits on both sides of it. If you don't have digits before it, you have to have a digit after it. If you do have digits before it, it is okay to not have digits after it. If there's a preceding digit, then you can just start accepting right away. More digits is okay. And then you have this optional exponent and a little bit of filling in at least one digit to get to an accept on the exponent. Okay, so that's how these things work. Do I have anything else I want to talk about today? Identifier examples, integer literal examples. That stuff. Don't really want to talk about that stuff. That's actually a really good place to call it a day. That's pretty much ending chapter 7 on the grammars and finite state machines, the recognition level of compiler work. Pretty much any compiler you ever use has a finite state machine built into it that does the lower lexical analysis, and it has another piece of code that implements an understanding of the grammar called the syntax analyzer. We haven't really looked at how that would be coded. I don't think we're going to. But there is a fairly mechanical way of doing that. These things have lots of uses beyond just the compiler. At the electrical level, I can use them. I've got a sequence of bits coming in from some device. I can use something like this to recognize it. This is a recognition protocol, ultimately. And so just a wire with bits coming in, I can use this to recognize patterns that I'm looking for. And as we start looking at the circuitry of the machine, we'll see that that is occasionally useful. I mentioned already your modems would have something like this inside to handle processing changes. Each transition would have an output attached to it, so that whatever the input, whatever's happening in the input, the output is following along. I need to look at your homework for just a second to see whether or not I required something. Did I share my screen with you? No, I didn't. Let's share it so you can see it too. Okay, so this is already posted out there. Go away. First question, give a grammar for the language of function prototypes. I already told you that. So function prototype has a return type. It has an identifier for a name. It has a parenthesis. It has a type. It has an identifier for variables. Okay, the parameter list, if it's empty, it should have a void in it. If it's non-empty, it has one or more parameters. It's simply a list of type parameter pairs repeated. So you're going to use that pattern we've seen for repeating it one or more times with a comma between each one and a semicolon at the end. So basically you want to produce a grammar that produces that. Don't worry, you can use what I did in my example for identifiers. So technically it would accept int here as well. Let's just let that one go. During the break, I rewrote it down here to say, don't worry about those kind of weird issues. The only infinite loop that you need to worry about is the parameter list. Everything else is kind of fixed. You get one of them down the line, okay? Identifiers are conceptually infinite, but I gave you the code for that. I gave you, okay, code. I gave you the grammar for identifier. Plug it in here, plug it in each time that happens. So you're going to make a grammar for that. You're going to make a finite state machine. Okay, I did not ask you to do any outputs on this machine. As I mentioned, you can tag onto the transitions outputs to other things, and that's not the case. So you're going to take your first name, whatever it is, and you're going to make something that does one or more repetitions of your name separated by 2 letters. Okay, those can be any letters. So that can be anything from AA, AB, AC, AD, BA, BB, BC, BD, whatever. One or more of your name, and you stick in the separators. This one looks kind of weird. There's Jim. There's the two letters RP. Okay. There's another Jim, And even though that looks like some kind of a weird error, simply the between letters are M and J. Those are perfectly valid letters. So I want you to make a machine that recognizes this. Do the left to right thing. Mine would be JIM, and then any two letters and start over. And then pick which states are going to be the accept states. So that's a pretty simple application of the finite state machine. This is due in 2 weeks. I don't remember if I talked about that before or not. This is not Hester being a total jerk. Yes, I am, but that's just beside the point. It's due in 2 weeks, people, 14 days. Okay, so even though it does happen to span over spring break, spend 7 days. Normally I would say spend 7 days going to the beach. Don't do that. Spend 7 days cowering at home, playing video games or something. And then spend 7 days working on the homework, or do the homework for the first 7 and take it easy for the second 7. Point being, you have 2 weeks. This is a 1 week homework. Okay, I'm simply ignoring the 7 days of spring break and saying, this is due at our next class meeting. I will be available throughout the next 14 days for email questions, and if necessary, we can even set up Zoom meetings if I'm near my computer, which I am most of the time because I'm staying home too. But yeah, the rest of you, we're not meeting next week. If you have any other classes, they're not meeting either. Questions on anything? Oh, do you prefer the homework as digital note? I don't know what note means, but I do prefer digital stuff. Basically, easy ways to do this would be, the first one is just letters. I mean, you can do that typed in a text box. The other homework answer, you could do it using paint. You can draw circles and arrows here. If you need to for this one, as long as it's neat, I'm okay with drawing it by hand, neatly, clearly labeled, and then scan it preferably, or photograph it under excellent light conditions and focus otherwise, and give me that picture. Okay, this is definitely, excuse me, the one down below. The state machine definitely leans towards a picture. So if you want to draw, my solution is drawn using paint, just so you know. It's not that hard to do, and it beats the heck out of photographic stuff. But I will accept any standard picture format here, whether it be whatever paint produces or a photograph if you must. Make it very good scan of that photograph so that I can read it clearly. If they're both in the same file, that's fine with me. If they're in separate files because one is typed and one isn't, that's okay. I can bring the two together pretty easily. So not a problem there. For both of them, I do prefer a PDF if you know how to produce that from what you have. It just saves me extra steps. I'm spending about 2 hours, maybe an hour and a half on each of my classes, just converting the homework submissions into that PDF that I give you back for feedback. So anything you can do to cut out some of that additional time of mine would be appreciated. PDFs will be, I'll be in a good mood while I'm grading your homework. I'm not going to make it required yet, but it is adding a chunk to my grading load, just in terms of producing PDFs that I can get back to you with annotations written on it. Okay, I'm done unless you have anything else to say. Anybody? I'm stopping my share. Have a good spring break. You too, all of you. Have a good spring break. And again, I am reachable if you need help whenever you decide to work on this. You know, anytime during the 2 weeks, I will be available for this. So feel free with that. Email is probably the fastest way to get a hold of me because I'm not going to be sitting in front of my computer most of that time. If I'm grading, I will be actually. But email is probably the fastest way to get my attention, and then we can decide how best to communicate after that. I am not opposed to a private Zoom meeting if that's what we need to do. frankly, we can do a lot with email. It gives me a chance to give you a good answer if you write me a good question. But if we need to meet the other way, it's an option. So I'll see you whenever. Have a good spring quarantine, everybody. Yeah, exactly. That's pretty much what it's going to be. I'm going to be sitting at home, probably playing some video games. I got some grading to catch up on because now I've got your test and a homework for your class. One other class, I have a test and a homework. The other two classes, I only have 3, I think. One of them, I got everything graded. I got amazingly lucky on that one. But I still have this week's homework for them. So I got 2 weeks to do it. I should get caught up. I'll talk to you later. Goodbye.